session here at Stanford. So so I just want to do a quick introduction and then start things. So if you remember bars last year, this is how it looked like last year. So there was a pandemic and there was fire, and this is not like nice lighting. This is actually the smoke, if you remember last year, San Francisco. But we ended up actually holding it last year virtually, and we had some good attendance. So we had like 200 simultaneous viewers at the peak, and then we had 2.5K views afterwards. So it was great, like doing it virtually, seeing you guys all virtually, but we are excited to see you all in person today here at Stanford. So let me tell you a little bit about bars today, and then after that we can get to the schedule. So before we get started, as you all know, COVID-19 is still a thing. So let me just go over our guidelines. If you're inside of this room, you probably already know this. So you got to be fully vaccinated, or you should have a negative COVID-19 test within the last 72 hours. Some folks might be watching this virtually right now and come in the afternoon, so I'm telling this for them so they also know this. In addition to that, everyone should be wearing masks inside. Outdoors is fine if you want to take your mask off, but indoors, please wear your mask even if you're a speaker. All right, so what else? So we have a number of sponsors. So we really appreciate having an awesome number of sponsors. Our gold sponsor is Ambi Robotics here right in the back. We also have a number of silver sponsors, Intuitive, Oris, Waymo, and Dexi are all in the back. And then we have our bronze sponsors, Baidu, Google, Aurora, TRI, and Multiply Labs. So they're all here, representative from these different sponsors are all here, excited to talk to you all. So please talk to them during the poster session. They're in the back, and they can talk to you. They're excited for you all to be here. A few other logistical things. So Wi-Fi, you can use a Stanford Visitor or radio-roam. I think that should be straightforward to connect. Posters. So if you're a student and you're presenting a poster in the first morning session, you should be setting up your poster already outside. If you haven't done that, please try to do that before the coffee break. And then if you're in the afternoon session, set up your posters during the lunch session. So there are easels outside. You should be setting it up. Your names should be on Post-its there. So, and if you have any questions, try to find Sid, and he will help you. All right, so we are also going to have a set of student respondents to ask questions. There's a microphone right over here. So please try to line up at the microphone if you have any questions from the speakers, or if you're a respondent and you want to ask a question. We have very limited transition time, so it would be great if you can just be there. All right, so bars this year. So how does it look like? So we got sold out. That is exciting. I hope everyone actually shows up. I think some people might be watching it online. It is an in-person event, so you're not holding this virtually, but we are streaming it with a delay. So who's at bars this year? So we have 281 students, so the large majority of people here are students and postdocs. We have a number of folks from industry, and then we have 27 faculty who are here. We have 2 keynote talks, 19 faculty talks, 9 sponsor talks, and 44 student spotlights. We also have a small number of students, high school students from the Robotics Club at Berkeley High and Oakland Tech in the group who are watching. All right, so in addition to all of these, this year we are also going to have 2 tables in the back for Black in Robotics and Inclusion in AI. So they're setting tables at the back close to the sponsors. So if you're interested, go talk to them. They're excited to talk to you, and that's why they're here. All right, so let's talk about our program. So the most important things on the program are the coffee break and lunch break. So coffee break is at 10:30 to 11. That is when the first poster session is, and that's when you can also talk to the sponsors. And then the second coffee break is 3:45 to 4:15. That's in the afternoon. That's sponsored by Ambi. All right, so we have a lunch break that is at 11:45 to 1:15. It's an hour and a half. It might seem long. It's not that long because we are on a farm and it takes a while to walk to anywhere. It's not like Berkeley. So if you want to find lunch places, it does take a while to get to lunch places. Here is a map that was put together by my students for suggestions on where to go. So there are a few walking options. So you could go to Stanford GSB, which is pretty good. I've been there. It's very good. There are a bunch of other places on the map too, like Coupa Cafe and Jimmy V's Sports Cafe. There's another Coupa Cafe close to Green Library. It kind of has a feel of the free speech movement, like cafe at Berkeley, if you want to get a sense of that. In addition to these places, there are places that you can Uber to, like they're 5 minutes, and they have really good options. So you can go to downtown Palo Alto on University Avenue, so that's 5 minutes Uber like that way, or California Avenue, 5 minutes Uber the other way, or you can DoorDash from them. There's also a 15-minute walk to Town and Country Village. So you can also go there. So in general, if you don't know these places, my suggestion is find a Stanford person and tag along with them. That is probably the best idea. All right, so that is lunch. Try to be back by 1:15. It does take a while to get here. So try to just like make sure you're back by that time. Faculty, we have a lunch get together like usual. So it's going to be at the Fisher conference room at the end of this hallway. So let's just meet up there afterwards and then we'll figure out where we are going. All right, so that was lunch and coffee, the most important parts of the schedule. In addition to that, we have a number of faculty talks. So like usual, the faculty talks, they're going to be 6 minutes plus 2 minutes questions. So we have quite a bit of time for questions. Feel free to ask questions. Again, line up at the microphone there if you have questions. That's probably the best way of doing it. If you're a faculty and giving a talk at a session, please come and sit at the front right here and you can get mic'd up so we can have like an easy transition time. And you can use your own computer. There are dongles here you can connect and hopefully that will all work okay. And then we are going to have 2 student and sponsor spotlight talks immediately after faculty talks like usual. And then we have 2 keynotes. So I'm really excited that today we are going to have Percy, Liang, and Reish giving our keynotes, talking about foundation models, and also talking about ethics and development of smart machines by Rob. So that is going to happen immediately after lunch. Again, please be back at 1:15. As I mentioned earlier, talks are going to be streamed online, but with a little bit of a delay. So you can use that link. It's going to be on YouTube. Only if faculty or speakers in general like agreed with that. So some of the talks are going to be streamed online, some are not. And then with that, I'd like to just thank my co-organizer. So I'm Dorsa Sadigh. I'm chairing this session with Mark Mueller up front here. He's co-chairing the session. And then we have 3 other awesome co-organizers that really made this thing happen. So special thanks to Erdem Beek, Sid Karamchedi, and Carrie Peterson. Can we do a round of applause for them? Basically, anything that is happening today is because of them. So if you run into them, just thank them. They've been amazing. And then also I have the whole Iliad lab today, helping out with everything. So there are other people who are helping out. Really appreciate all your help. And then with that, I would just like to thank the sponsors again and switch to Mark, who is moderating the first session. And we can have our first speaker come and set up.
Is this on? Yeah, there we go. Good morning, everyone, from my side as well. I'm introducing our speakers. Karen gets to go first. We will have timing from the front, so we'll try to keep everyone honest. We have found the meanest looking grad student we could. So Karen, if you are connected, then ready whenever you go. For questions, there's a mic over there, so you'll ask people to just come to the front, to the microphone there if you have questions. Discussion is always sort of the most fun part, so please feel free to ask questions if you do have them. Go ahead. Will the slides be posted? I don't think so. If you're interested in slides, I recommend you just contact the speaker by email and ask them. Okay, Karen, over to you.
All right. Good morning. I'm Karen Liu. Welcome to Stanford. 2 years ago, I gave a talk at BARS, and the title of my talk was Sim-to-Real for Physical Tasks Involving Humans. Well, after 2 years, we're still solving the same problem. I guess there's no surprise there. If you recall, this is a slide also from 2 years ago. To achieve robot-assisted everyday task, we need to have a really good controllers, which means that we need to have a good human models as well. But one thing I didn't talk about 2 years ago was the role of physics simulation, and that's what I'm going to focus on today. Physics simulation is particularly crucial for physical human-robot interaction because it provides a very nice, safe, and inexpensive virtual playground for robots to learn their motor skills. But most robotics researchers treat physics simulator as a black box and rarely attempt to improve this black box. The rationale is that the simulator is not meant to be trusted, right? And any robotic progress should only be measured in the real world. Indeed, these simulation techniques we have today only focus on producing realistic visualization and show very little evidence that it can really predict the outcome of a sequence of actions in the real world. But what if we allow the black box physics simulator to learn from the real world so that it can be better at predicting the real world outcomes? Ideally, we would love to have a learnable physics engine that only takes a small amount of real-world data, and then we can customize this engine, use that to train our policy, and hopefully the policy will be better at sim-to-real gap transfer. So our first job is to identify all possible places in this physics simulation that can be made learnable from data. For example, maybe we can learn a contact handler that can predict contact force, or we can learn boundary conditions that can enforce more accurate range of motion and actuation capability for the robots. So obviously, the first place we should be looking at is the simulation parameters, mu. In this example, we want to make our simulators more expressive, so we construct a hybrid simulator combining a learnable neural network physics and the physics equation. So those parameters, mu, used to be just manually determined constants. Now we're going to make them stay action depend function. And we chose to learn parameters in the contact models and actuators, because those are the parameters usually really difficult to measure from the real world. And the models we use in physics simulation is just known to be a really poor approximation. So here's our evaluation simulation. We use the initial policy to collect some data of the robots walking on this bouncy mattress. The initial policy doesn't work, but that's okay. We just want to use those failed experiences to train our physics engine. And once our physics engine is customized, we can use that to train a real policy we care about. We can also make the bounds of a stay and action spaces learnable. This is particularly important for assistive robotics. We really need to have a good simulators for humans, such that when we train our robots with this virtual human in simulation, those robots can be more effective and safer when deployed in the real world. So how do we make the human simulator better? For example, from biomechanics literature, we know that human joint limit is very complex. It's also state dependent. Therefore, we can learn a state dependent implicit function represented as a neural network to model the range of a human motion. And we can use real human poses as a training data. And once this implicit equation is learned, then we can enforce it as a differential algebraic equation in our physics simulation. We developed an open source software called Assistive Gym to provide a training environment for assistive robotics. And Assistive Gym features human models with learned joint limits and joint torque capabilities. We still have one more problem. This learnable physics engine is useless if we don't know how to optimize those parameters efficiently. So we can always use, gradient-free optimizers, but the problem is that it doesn't scale up when the learnable parameters is really large. It would be really great if we can have an end-to-end differentiable physics engine. And turn out that most part of this physics engine is already differentiable. The only questionable part is this contact handling. We could naively throw the contact problem to AutoDiff libraries, but it completely ignores the unique structure of our problem due to the contact dynamics. On the other hand, if we can really take advantage of the sparsity in the formulation of our contact handling, then we can really develop much faster and effective algorithm to compute gradients through this program called LCP. So we introduced a feature-complete and very fast differentiable physics engine. Here are some results of solving optimal control problem using a generic gradient-based solver called IPOPT. And you've noticed that all these problems involve contact switches, which are known to be challenging to solve using a gradient-based solver. We also open source our differentiable physics engines called Nimble Physics. You can pip install and play with it. Nimble is based on a fully functional physics engine Dart, and it makes Dart differentiable, but without simplifying how we handle contacts and without sacrificing speed. So finally, we can take our learnable physics framework make our learnable physics engine completely differentiable as well. And hopefully this will open up a lot of new applications, such as digital twins for robotics, for biomechanics, and for other engineering domains. And thank you.
Thank you, Karen. Any questions? I think we have some time for questions. Again, if you'd like to ask a question, best is if you can come up to the microphone. If not, I'm happy to monopolize the question time. So Karen, I'm curious, how do I, if I have a problem, how do I know whether my physics is learnable? Is there sort of any physics is learnable? Is it time invariant, no contacts?
Yeah, so I think this is a sort of design question, right? Like when we look at when we look at our problems, you kind of have to make a decision which parameters you want to make learnable. Ideally, theoretically, you can make everything learnable if you're, for some problems where your gradients are very effective. But oftentimes, you kind of have to make choices. And then, like the project that we're doing, we, contacts usually where we know that our approximation is not very good.
Excellent,
yeah.
Thanks. Any other questions? Quick one for him, but go ahead.
It's like awkwardly on the other side. I was curious about the scaling of your method. I know that these things scale really poorly, especially you showed Atlas, I think. So could you discuss how does the runtime scale with the size of the system?
Yeah, so the differentiable physics engine in general is still very actively developing research field, and I think that is the number one area that we're working towards too. We show a lot of good results with a medium-sized problem, but when you're ideally we want to be able to have this entire neural network be learnable, and that is the direction we're making progress towards.
Excellent, thank you. Right up next we have Ron Fearing from Berkeley. Ron, go ahead.
Good morning, everyone. Hope you can hear me through the mask.
people in the back want to come up front, feel free to come here. But I can start too. All right. Yeah, so hi everyone, I'm Dorsa, and today I want to talk a little bit about some of our work in trying to learn from interactions to interact better. And specifically, I want to spend a little bit of time talking about this idea of learning human preferences. I mean, in general, we have been doing a thread of work under this category of learning human preferences. But we have a recent work where we are trying to learn multimodal reward functions from rankings. And this is a work that is led by Vivek Myers and Erdem Biek. Vivek is, just a plug for both of them, Vivek is an undergrad applying for graduate schools. Erdem is a graduate student applying for academic jobs. So talk to both of them if you can during the coffee breaks. So I'm going to spend a little bit of time talking about that. And at the very end, I want to talk about how we can stabilize interactions and how that can enable better building better interactive and collaborative systems. All right, so this paradigm of having a person and trying to learn humans' preferences in general has been around for a period of time. We look at learning from human demonstrations, comparisons, physical feedback, and we try to learn this model of a reward function. But oftentimes, our data is not as clean as I'm showing here. Oftentimes, our data is coming from a group of humans. We often have a mixture of preferences coming from different types of humans, and each of them might have a different underlying reward function that represents that. So ideally, my robot should try to capture these different reward functions, a multimodal representation that captures these different preferences. And that's a problem that we are interested in. And of course, this has been around for a long period of time. People have thought about multimodal learning reward functions from demonstrations. But in general, expert demonstrations are also pretty challenging to collect from humans. So another source of data that's pretty powerful is pairwise comparisons. Me showing two different trajectories and ask a person, which one do you prefer? And there's quite a bit of work in this domain, but mostly focused on unimodal reward functions. So the question that we were interested in was, could we tap into these different sources of data, like pairwise comparisons, and learn a multimodal reward function? Like, for example, can I show two different trajectories and then have a population of different reward functions and learn that multimodal representation? It turns out the answer is no. So if I have a setting like this, and I have a pairwise comparison from a person saying I like 1/2, and then the robot trying to learn something from that, another person can simply come in and say, well, I like trajectory 2/a, over 1. And then that could create this inconsistent data for the robot that makes it really difficult for the robot to learn a multimodal reward function. So actually, theoretically, it is shown that learning from pairwise comparisons is impossible when you think about learning a multimodal reward function. So the question we are interested in is maybe we can expand this idea of comparisons to rankings. So what if I have rankings, full rankings between the demonstrations, and from that, maybe I can learn a multimodal reward function. And that is really what this work is about. I'm skipping a lot of details here of how we do it, but the paradigm is I'm going to show basically a bunch of set of trajectories, and then I'm going to ask a person to rank them. Different people might come in with different preferences and underlying rewards. Each one of them has a response model, and with some probability, they're choosing a ranking. And we use the loose choice axiom here to capture the human response preferences. The thing that at the end of the day, the robot sees are just the rankings. So the robot gets the rankings, and from those, it should try to recover the reward functions. Again, skipping a lot of details here, but the way we do that is you can write the posterior using the Bayesian update, and you need to compute this likelihood, and we show that we can actually compute that likelihood using this loose choice axiom and expanding out these probabilities, and we get a multimodal reward. Then the interesting question to ask is, how can we actively generate new questions to the user and ask them these ranking queries? And that's an interesting active learning problem that we have also explored. So instead of just randomly showing a bunch of trajectories, maybe we can actively look for the most informative set of trajectories and ask a person to rank those. And again, skipping the details there, but we can actually demonstrate the active method outperforms the random sampling method, even in these ranking settings. All right, so that kind of brings me to this human preferences. In the last 1 minute, if I have time, I want to very briefly mention how we use these human preferences or models of humans in interaction. In general, we might have a reward function. We might have other representations like latent intents or latent representations of the human partner and use those for coordination. So here's an example. Imagine that you're in a room. It's a messy room, and you want to clean it with a partner. Okay? So one thing you need to do is you need to build a model of the partner. The partner is non-stationary. They're changing their behavior in response to you. So you have to actually capture that non-stationarity. In addition to that, you need to learn how to clean the house. So you have kind of like two tasks almost, like figure out how to clean the task and figure out what your partner is really trying to do here. And that ends up being pretty challenging. So instead, wouldn't it be easier for us to kind of lock our partner in a room and then get the partner, do the thing in the room, and us just focus on the task of cleaning? It becomes a single agent problem. You remove non-stationarity, you reduce non-stationarity, and maybe that is an easier problem. So it sounds like a silly idea, but it actually works in practice. So we have a choral paper on this where we are learning these representations of the partner, and we are stabilizing the partner. We are fixing the partner to make the task a lot easier. And it turns out that it actually works across a number of domains compared to a set of baselines. Our algorithm is called SILI, Stabilizing Influencing Latent Intent. Yeah, and the reason I'm excited, this is my last slide, the reason I'm excited about this is that I think this has more general implications. If you think about bimanual tasks, like cutting a steak, the reason that you hold a steak, the whole reason that you have the other arm holding the steak is so it stabilizes the steak, so you don't worry about the non-stationarity. You have a simpler dynamics to predict. You don't need to predict where the steak flies around. And this idea of reducing non-stationarity and stabilizing either the environment or the partner, I think in general is pretty powerful and could be used in these bimanual tasks too. So with that, I can take any questions if there's time.
Thank you, Dorsa. I think we've all wanted to lock our partners up while cleaning a little bit. If there are any questions, please come to the front. So how do you make this decision to, when is it more efficient to lock up? Of course, there's efficiencies of cooperating, right? So how do I think about that problem?
Yeah, no, that's a good point. And null set, it doesn't make sense to do that in all settings, right? So there is a balance, and it depends on how much of the task requires the partner to work alone and how much of the task requires this coordination. So it does become like task dependent, and we have a parameter that basically modulates between the two. But in practice, right, like if the partner can do part of the task, it's kind of role assignment. So how can you get emergent role assignment? But the way we are doing that is by stabilizing these representations to actually get emergent role assignment. Yeah, it's interesting to see it in these bimanual tasks. I was excited to see that shows up in practice too.
Go ahead.
Hi, great talk, by the way. So you moved to a ranking-based system for the preferences, but is there still a way to specify that something is still equally desirable, so like the same rank, or do they always have to be, one is better than the other?
That's a good question. Yeah. So we are not doing it necessarily in this work, but I think you can bring that in this work too. Like we have done like prior work where we have pairwise comparisons and a confidence assigned to them, or like some measure of like how much these preferences are actually like equal or like different. But we haven't done it in the ranking-based setting. I think it would be interesting to extend it, but we haven't done that. We'd love to chat about it offline.
Thanks.
All right.
Thank you, Dorsa. Up next, we have Hannah Stewart from Berkeley.
Thank you. And it's great to be here today. I'm Hannah Stewart, and I've been at UC Berkeley in mechanical engineering for almost 4 years now. And I run the Embodied Dexterity group, which focuses on electromechanical design for more dexterous robots that do physical interaction. And so how do we create more capable machines? First, we actually start from the physics of interaction and creating new models to better understand complex contact conditions. So for example, if your friction can dramatically change very quickly. We also develop new ways to sense touch, and this is that we can sense and respond to those changing contact conditions very quickly. And then finally, we take what we've understood about the physical interaction to create new mechanisms with embodied intelligence. Now, this has a wide range of potential applications. On the left-hand side, you can see robotics works, where we're developing autonomous or remote systems. And on the right-hand side, you can see systems that are actually worn on the body, and we look at human physical robot interaction to better design capable human manipulation. Now, within the last year, we've had manuscripts come out for 4 new projects, and so I want to highlight them today. And I'm going to focus most on the most recent work. Now, vacuum suction grippers are a very common solution in industry, and it's because they make a lot of sense. You can grasp objects from just one side. However, suction grasp failures can occur quickly, and they can sometimes be very hard to predict, both in planning and execution. And so some works have tried to combat this with feedback with tactile sensing. Now, some technologies put electronics in the cup itself, which creates some fabrication complexities. Others try to measure it remotely through observing deformation or through measuring the pressure in the suction line. And that's awesome for a true binary suction measurement to tell you whether you're successful or not. But it lacks the ability to tell you about a more analog, detailed information about the state of the grasp. So we're combating these shortcomings with a new smart suction gripper. Now, as you can see on the image on the left, it has no electronics in the cup itself. However, it has these internal chambers. Now, we're going to measure the wall pressure of those chambers using a remotely located pressure transducer. And with this, we can now compare the flow rates in between these chambers to get a sense of internal flow. And you can see the importance of this in the video, where as that seal starts to break, flow is going to go along that white line. And in fact, we're going to get the maximum flow rate in the channel opposite to where the failure occurs. And so with this, we can localize where around the perimeter that failure happened. And in collaboration with Professor Ken Goldberg's group, we've also shown that we can successfully predict when this failure is going to occur before it happens, and so that we can prevent that failure altogether. Now, we've also in this paper explored how we can use a suction cup for haptic exploration, which is not a typical modality for this kind of gripper. In this particular circumstance, we've reduced the pressure, so we're gently sucking onto the surface and allowing for gentle sliding. And as we go across the rough, bumpy surface on the left, we get only partial engagement with our suction sensor. And then when we go across the smooth, flat section, we get full engagement. So this lets us, for example, check before we lift an object if we have any texture or porosity that might compromise the strength of our grasp. And so these sort of very rich pieces of information, I think, are extremely powerful and could really change the way that we're performing and thinking about feedback in suction grasping in a very inexpensive and resilient fashion. And so I think that this has some great potential. So it is patent pending, and we are hoping to license it out. Now, one of the other areas that we've recently had some interest in is manipulation in granular materials. And we're finding this really fascinating because granular materials are all over the place, from sand outside to rice in your cabinet. And in short, granular resistive force theory is a very useful way to model forces as bodies intrude into granular media. But prior work has limited this modeling to a 2D formulation. And this isn't necessarily helpful when you have manipulation in many different directions. And so we characterized the third dimension, and we introduced the first true 3D generalizable implementation for this method. And you can see on the right-hand side, one bio-inspired sort of validation test that we did, inspired by the wiggling motions of mole crabs digging down into sand. And now with my last minute, I do want to mention at least the two works that came out in human-robot interaction, which I think are really nice. The left-hand side has a poster today, so check it out. And it's looking at grasping with the back of the hand, which has some real advantages for people with tetraplegia, spinal cord injury at the C6, C7 level. And on the right-hand side, we performed a study to try and investigate the kinesthetic haptic benefits of having a shoulder-driven, body-powered prosthetic, and trying to understand why we see high performance in these systems as compared to more motorized bioelectric versions. And with that, I want to thank the researchers in the lab who really get this work done, as well as the funding sources that make it possible. And I'm happy to take questions.
Thank you, Hannah. I see you have a question.
Thank you. That was super exciting. I was wondering if you think that suction, even on fingered hands, could be useful, because you mentioned you can use it for exploration. And how would that interact with planning manipulation in the sense of actually using the fingers versus also having suction on the fingertips?
Absolutely. Yeah. So suction is giving us what's called astrictive grasping, which means you're able to pull on a surface. And most in-hand manipulation models don't assume that you can do this. And so I think that really that change in contact conditions does kind of open the door to new possibilities like palming surfaces or palming a ball. And in fact, you can use fingertip suction flow as a very useful tactile sensor. And I would recommend it for people who have the ability to pull a flow.
Any other questions? A very quick question. 4 chambers, why 4?
Yeah, it was a very sensible first place to start, although that isn't, you could have 3 or you could have 5, and that's something that we're going to investigate in future work.
Okay, excellent, thank you.
Thank you.
Just before I introduce the next speaker, I want to ask that everyone who's participating in the first spotlight session, so that'll be the students and the sponsors, that you please line up on the far right-hand side of the room. Please line up in the order that you will be speaking, just so the flow is smooth. These spotlight talks are often a little bit stressful. So I want to just encourage all the students and the sponsors, please start lining up on your right-hand side of the room so we can have that run efficiently. And then our last speaker for the session today, Allison Okamura from Stanford.
Great, thanks so much. Thanks for organizing, and it's great to be back in person. So I'm excited to give some updates on projects that we've done in the area of social touch, which is something my lab has been working on for a while, but this of course really came to a head in the era of COVID and being physically distanced. And so we have a lot of questions about how do we use haptic technology, wearable devices in order to allow people to communicate when they are remote. So our goal is to be able to have wearable haptic devices which allow this communication. And this communication can happen in a number of different dyads. So one example would be between humans and humans. Another would be between humans and agents. Of course, this has nothing to do with physical distancing, but naturally, like when I'm driving, I'd rather not just have my haptic feedback be used to call my attention to some visual channel, but rather I would like to have the haptics actually provide me with information so I don't have to be distracted and take my eyes off the road. And in addition, as robots become more ubiquitous around us, we need better ways of communicating with them that might be more related to the natural communications that we're used to using with people. And we're interested in how you can make this connection in a physical manner. So this talk is going to specifically focus on social touch. So our interest in being able to communicate social emotional information. And of course, when we interact with people, animals, or even a nice warm cup of coffee, this can make us feel good or bad depending on the form of the physical interaction. We're focusing on the good here. One of our big challenges in this is that the sort of neuroscience of touch in different places on the body is not completely well understood. We do know, however, that the distribution of mechanoreceptors or tactile sensors embedded in our skin is much more sparse on the arms and other parts of the body compared to what we have in the fingertips. So although most haptic devices are designed to be worn on the hands, we want to move away from the hands so that we can still use our hands to do other things, but that means this challenge of dealing with haptic feedback on other places on the body. In addition, there's this somewhat subtle issue of active versus passive touch. And this is also a problem for autonomous robots trying to use the sense of touch. And the issue here is that a lot of the way that we receive tactile information is through us stimulating the environment and receiving a response. And our hands, our bodies are designed to use our hands to explore the world. But the feedback, if it comes in a different location, we don't necessarily know how to explore the world in order to get the desired feedback in other locations. And so if we just think about passive touch as haptic feedback coming into our bodies without us doing something in order to generate that feedback, it becomes more difficult for the person to pay attention to it and to understand it. So to address these challenges, we've started exploring some specific types of applications in social touch. One of the newer mechanoreceptors that's been discovered in the skin is called the CT or C-tactile afferent, which when your arm is stroked actually makes it feel good. So it's kind of thought of as the social touch mechanoreceptor. And so we've tried to effectively stimulate this kind of sensation using different illusions for feeling a stroke on the skin. So to avoid the idea of taking a robot finger and literally dragging it across the skin, we want to have some kind of haptic illusion, which will use different discrete contact points. When we time it right, we get the forces just right and the distributions just right, it will actually feel like a continuous stroke. And we've been able to show that's the case with several different types of devices. Then, in order to actually move this into a real social touch display, we recently finished a project where we recorded tactile information when people interacted, and then we turned around and displayed it. So first, we had groups of participants, sets of 2 participants, where one would wear a capacitive array tactile sensor on their arm, as Sophia is wearing there. And then we had some various social prompts, like we would tell my other student, why don't you touch Sophia in a way that tries to convey happiness or tries to convey trying to get their attention, different types of cues like that. And then if you lay out this capacitive tactile array sensor, we can measure those different patterns from these types of touches and come up with learned models for how people interact with the sense of touch. And then we could display them on one of these patterned social touch devices that someone would wear on their arm. Now, clearly, this is not yet ready for commercialization. There's still a lot of work to be done in terms of the devices and how to make them, truly wearable and deal with batteries and all of that. But at least here, what we've been able to show through this sparse display is that you can indeed convey these social touches. And on the left, you can see that the main aspects of social touches can be displayed. So for example, let's say someone is interested in conveying attention. That is a type of touch that has high valence and high arousal. And indeed, our subjects rate when they feel this from the device that they feel relatively high valence and arousal. Then there's the idea of being able to recognize what is the nature of this social touch. And these are examples of what was rendered versus what was recalled. And you can see that the overall accuracy is not great. You might look at it and say 45%. That's not so good. But interestingly, that matches very closely. It's about a 50% accuracy when you have humans and humans doing social touch communications and they don't know each other. It turns out it's way higher when the pairs of humans are very familiar with each other. But when they don't know each other, this is about the number that you get even from human touch interaction. So this is kind of actually what you'd expect then, right? Because we're communicating from a device to a human. All right, I'm going to just end with one last note on something that we just submitted about haptic hugs. We have created devices that provide sort of detailed pressure in different locations of the body and have shown that people can perceive these. And this was in collaboration with Honda Research Institute, where they're building a hugging robot and would like to have haptic feedback for people who teleoperate it. And with that, I want to thank all the awesome students and sponsors that have contributed to this work. Happy to take questions.
Thank you, Allison. If there are questions on this side of the room, let me know and I can come with the mic. Otherwise, please line up there. Go ahead.
Thank you. So I have a question. Other than just the touching event, I think the body temperature from the other person is also important for the social. How do you achieve that? How do you think about it?
That's a great question. Is there feedback? So at least in the wearable device for the arm, we've only sort of displayed the touches as if they were kind of haptic icons, or it's like sending an emoji. Maybe a haptic emoji is a good analogy, which is of course not really interactive. But you could imagine teleoperating these social touches as well so that both sides can feel and display, in which case you would need a kind of sensor where someone can actually input information that could be sent in real time.
Hi, great talk.
Thanks.
I was wondering, what type of actuators do you use for the haptic devices typically, and what are some of the challenges in terms of actuation for haptics?
Yeah, that's a great question because I completely glossed over that. So primarily for wearable devices, we've been using vibration, small voice coil motors like little speakers is what's in the arm device, and also pneumatics. But I think this is a huge challenge for the field in terms of how do you make these things lightweight, wearable, low cost, and have long battery life. And it's much more challenging, the wearables that only relate to sensing, because we actually have to provide actuation power.
Thank you.
Okay, one more question if it's very fast.
Okay. try to be quick.
I'll try to make it fast. Have y'all considered applications for people, for example, like on the autism spectrum who have issues with nonverbal communication?
Yeah, that's a great question. Absolutely, we've considered the role of social touch and various pathologies and communication strategies for all kinds of different groups. With autism, it's interesting because you also have some tactile oversensitivity as well, and it tends to be very individual specific. But we would like to work that out and understand how do you do a kind of person-specific display that's most comfortable for them.
Thank you.
Thank you.
Excellent. Thank you, Allison. And with that, I'd just thank all the speakers in this first session. And then I'll hand over to Sid for the spotlights.
Hey folks, I'm Sid. I'm a PhD student with Dorsa and Percy, and we have a lovely array of student spotlight speakers. It's going to be pretty tight. They're going to be a minute each. We should maybe practice like one clap between just to keep the timing on schedule. No clapping? All right, Mark says no clapping. But all of the students are going to be having poster sessions outside, I think, following this. And with that, Michelle, you can take it away.
Hi, everyone. My name is Michelle. I'm from Stanford. And today I'll be presenting our work on learning universal controllers with differential physics for online system identification. So the problem that we're trying to tackle is trying to develop agents that can adapt to unknown or changing environments. So for instance, we want a quadruped to walk along a surface with unknown friction properties, or we want a robot to throw an object with unknown mass. And the way that we tackle this problem is by combining a universal controller with a differential physics engine. And our controller is universal because it's trained on a wide range of environments. And then at test time, we use a differential physics engine to continuously estimate the physical parameters of the environment in an online fashion. And our results show that we're able to outperform domain randomization and also domain adaptation methods that rely on learned system identification modules. If you're interested in learning more, please come check out our poster afterwards. Thanks.
Hi everyone, my name is Sarum Kim from Biomimetic Melee Systems Lab at UC Berkeley. And today I'd like to introduce our flexible robot which can locomote on a surface to overcome diverse types of terrains. This was inspired by traveling buckle on the ground, like the rock in a rug rolling down the inclines, and then consists of 3 different steps of motion of growth of the buckle at the root and propagation along the flexure and releasing when it arrives at the end of the flexure. So please come to check our poster for more details if you're interested. Thank you.
Hello, my name is Conrad, and I'm from the Biomimetic Melee Systems Lab at Berkeley. My research focuses on capacitive pressure sensors that can be arrayed across aerodynamic surfaces. These are inspired by things like birds and flying insects because you see these insects and birds have sensors across the entire body rather than just a centralized location like airplanes nowadays. And so these pressure sensors have to be very sensitive because, as you could see on the top right, the pressure drops only minimally when you're flying very slow speeds like robots nowadays. And so essentially what my pressure sensor does is it was designed and optimized so that we could detect 10 pascals. And it's right there, and it's manufactured from a flex PCB lattice, which is a spacer, and a membrane, which also acts as a shield. If you have more questions, come please see me at my poster. Yes.
Hello, I'm Adam from Stanford, working with Dorsa Sadigh. My research is about efficiently modeling human preferences to develop robots that can interact better, for example, learn from or teach humans. Consider as an example a human who has a policy or an objective in their minds, but the robot doesn't know this objective. It can be how this human wants to drive a car, optimize gait parameters of an exoskeleton, or operate a robot for some task. We leverage different sorts of information that we may get from the human. For example, demonstrations, comparisons, or more expressive forms of comparison feedback, such as rankings or scale. Using these information, the robot can learn the policy or the objective. It can be a non-parametric model like Gaussian processes or parametric models like neural networks. We also have the robot query the user to refine its learned model. At the end, we use these learned models to achieve decentralized cooperation. Moving forward, we are now flipping the equation and developing agents that can actively teach each other. I'm looking forward to discussing this more with you.
Cool. Hi, everybody. My name is Sunil. I work with Dorsa. Oh, next slide. That's a good idea. Okay, let's see. Yeah, so sorry. My name is Sunil. So there are roughly 12 million people in the US with motor impairment disabilities, and robots have the potential to assist these people in their daily lives. In our research, we study robot-assisted bike transfer. So existing approaches rely on predetermined robot trajectories for a discrete set of food shapes. Our approach is the first to be agnostic to how the food is acquired and to work for a continuum of food shapes. So we're also the first to formalize comfort and efficiency for bike transfer, which enables safe and effective trajectories. So we formulate comfort as personal space within a conical region stemming from the mouth, and efficiency as the volume of the final bite. So we model the real environment in simulation. So using the food state, we can sample collision-free goal poses, which is accelerated with the learned constraint model in simulation. We then cluster the goal poses and finally run motion planning to reach these goals with novel heuristic combining this comfort and efficiency. This pipeline handles arbitrary food geometries, poses, and mouth dimensions. We also conducted a user study on non-disabled users to safely evaluate our method end-to-end. So our method outperforms the baseline in user rankings and ratings of ease and comfort. Cool. Thanks.
Hello, everyone. This is Malik, PhD student from Berkeley, advised by Professor Hannah Stewart. Our research is about a new wearable device for people with spinal cord injury at C6, C7 cervical level, which generally result in tetraplegia. Although they lose their voluntary flexion of their finger and wrist, their wrist extension typically remains. So we developed a new device called Dorsa grasper. By using both active wrist extend and spinal finger flexion, we can grasp object with the back of the hand. And our Dorsa grasper can provide both power palm grasping and general pinching, and an artificial palm plays important role in maximum grip strength. As you can see in the figure in the bottom right, we show that a subject with spinal cord injury at C6 level successfully conduct the grasp and release test during human subject experimentation. If you are interested, please come to my poster. Thank you.
Previously, suction cup manipulation has relied on vision and assumed smooth texture and known inertia, which doesn't apply to many practical applications. Here we present a multi-chamber smart suction cup that can directly measure the local contact state of the vacuum seal. Using this suction cup, we implemented gentle haptic expiration with lowered vacuum pressure. Sliding expiration can evaluate the current texture, and palpating expiration can search for the surface normal and evaluate its graspability. The smart suction cup can also locate the suction brake seals in forceful manipulation. And we found the pressure distributions at the brake moment are closely linked to the brake location. And using LSTM network, we could locate the brake quadrant with 97% accuracy. Thank you.
Hi, I'm Zong Chua from CharmLab at Stanford. Haptic feedback in robotic telesurgery is difficult to implement due to strict requirements on end effector force sensors. Neural nets that use vision and robot kinematic and torque information inputs are a promising way of estimating interaction forces. However, little work has been done to characterize their real-time performance for haptic feedback. We evaluated the performance of multimodal neural net force estimates for closed-loop haptic feedback by quantifying the system impedance transparency and stability. We then tested the effects of refitting the networks with additional data collected under closed-loop haptic feedback. We found that our vision-only neural net was most stable, but least transparent in directions with low visual information, and its stability improves under retraining from closed-loop haptic feedback. If you're interested to learn more, come check out our poster. Thank you.
Hi everyone, I'm Negin Haravi, and this is joint work with M. Salvato. We were advised by Allison, Okamura, and Janette B from Stanford. Compelling mixed reality experiences with haptic feedback require that hand-object interactions occur smoothly and with minimal latency. However, hand tracking methods used by the popular VR headsets are usually insufficient for this because they're either too imprecise or too slow for this application, creating haptic instability. To address this, we propose the interaction expectation model, where based on a user's hand movement, we propose to predict into the future that interaction is about to occur before it has. Our model takes as input a series of hand poses as well as virtual object geometry, feeds it into a recurrent neural network, and predicts probability of contact. It is trained using the graph dataset. By calculating the minimum hand-object distance between the hand and the object and feeding these along with the hand poses into this network, we were able to successfully predict interaction before it occurs. For example, for a time window of 100 milliseconds, we had an error of 15. Please stop by our poster to hear more. Thank you.
Hi, my name is Sid Reddy, and today I'd like to present our recent work on building adaptive user interfaces for typing and robotic control. So our overall goal is to help users with disabilities better operate computers and robots using alternative types of input, like eye gaze recorded through an off-the-shelf webcam, or even brain activity recorded through an implanted device. And the exciting thing is, together with our collaborators at UCSF, we actually had the opportunity to run a pilot study with one patient who had an ECOG array brain-computer interface and wanted to use it to be able to select words on a screen. And we were able to help them improve the accuracy of their typing system at inferring their desired word, given their brain activity. And the key idea to enable this in the real world is reinforcement learning through online user feedback, through the user's natural interactions with the system. And in this case, we were able to treat the user's backspaces, which occur naturally as someone types and corrects, as negative reinforcement learning. And we're currently extending this approach to robotic control and other sequential tasks. So if you're interested, come check out our poster. Thank you.
Hi, everyone. I'm Andrea. I'm a PhD student with Claire Tomlin and Anka Dragan at UC Berkeley. Now, robots rely on predictive models of human behavior frequently to plan safe and efficient motions around people. Because people vary in their intentions and preferences and styles of behavior, these models have to adapt online upon observing a specific person. Consider this autonomous car that's using Bayesian inference to estimate if a human-driven car is going to take a left or go straight at an intersection. Now, these online adaptive models are necessary and beneficial, but they also raise new safety questions like, what's the best case time it could take the robot to learn the human model parameters? What's the worst case time? Or what are good initializations that the robot should use to guarantee it can learn effectively? Our idea is to model the robot's learning algorithm as a dynamical system where the state and the current parameter estimate are the current parameter estimate is in the state, and the control is the human data that the robot observes. Answering what model parameters can the robot learn and in how much time really reduces to solving a reachability problem. Come check out our poster and see how this analysis tool can help make robots safer in a variety of different domains. Thanks.
Hi, my name is Rika Antonova. I am a postdoc at the Interactive Perception and Robot Learning Lab at Stanford. And I'd like to share 3 things with you. One is the dynamic environments with deformable objects. It's fast, open source, extensible suite of environments that support loading thousands of meshes and textures. And second is our line of work on visual learning, where we make use of active learning and we use a particular structured policy to break down the representation for repetitive tasks and be able to learn from human videos without any additional labeling. And third, we have a few projects on real-to-sim where we use black box simulators and also starting to use differentiable simulators and differentiable rendering And I'm looking forward to talking with you about these topics at the poster. Thank you.
Hi, I'm Toki, and the work I'm presenting is grounding predicates through actions. Our goal is to detect symbolic predicates in images, the kind of predicates that are used in task planning. The problem is that manually labeling data sets to train predicate classifiers is wildly expensive. So our solution is to label predicates automatically with the pre and post conditions of actions. We start with videos of humans performing actions in the 20 billion something something data set. We then define pre and post conditions for each of these actions and use them to automatically label the predicates in these videos. We use this automatically labeled data to train predicate classifiers to detect predicates, such as whether a book is open or closed or whether a flashlight has fallen. We can use these trained predicate classifiers for closed-loop task planning on a real robot, where a task planner uses the detected predicates to solve long horizon problems. Thanks.
Good morning, I'm Santiago. In our work, we model an optimal control problem for the case of dynamics that may exhibit both continuous and discrete behaviors under the presence of a disturbance or attack as a zero-sum game. We formulate an infinite horizon optimization problem in which there is a player selecting a control action seeking to minimize a cost function under the presence of an opponent action designed by a player that wants to maximize the cost. Competing solutions is undoable in general. The hybridicity of the model may lead to non-unique solutions to the system, and the opponent action may render a set of interest unstable. This is why our approach is based on cost evaluation results. We characterize the solution to this problem as a Nash equilibrium, and we find bounds on the cost under the presence of disturbances and minimize the effect of the worst case attack. For more details, please stop by the poster. Thank you.
Hi, everyone. My name is Annie Chen, and this is joint work with Suraj Nair and Chelsea Finn at Stanford University. The goal of this work is to learn reward functions that can generalize to new environments and tasks. The reason we want these is so that such reward functions can provide the agent with knowledge of task completion, even in unseen situations. The key idea to our approach, which we call domain agnostic video discriminator, or DVD, is to train a discriminator that takes in two videos and outputs whether they're doing the same task. We train DVD on a broad data set of human videos and a small number of robot videos from an original training environment. Then at test time, given a demo video, the robot can use DVD to complete the task in unseen environments. We find that training using diverse in the wild human videos greatly improves task and environment generalization compared to only using robot data. Thank you very much.
All right. Hi, everyone. I'm Suraj, and today I'm going to be talking about our recent work, where our goal is to learn language-conditioned visual motor skills from broad, suboptimal offline robot data sets. And our approach to this is we're going to crowdsource language annotations of the data and use this to learn a language-conditioned reward function for offline reinforcement learning. And specifically, we take a model-based approach where we learn a visual dynamics model and use model predictive control to maximize this language condition reward. In our experiments, we find that with this method, we can directly reuse an existing data set, a replay buffer of a previously trained RL agent of a Franca robot over a desk, and learn language condition skills from vision, like opening the drawers and reaching to or moving different objects. And with that, please check out our poster for more information. Thanks.
See if this is playing. So there we go. I'm excited to present some recent work we're calling GRASP Optimized Planning for Fast Inertial Transport. In prior work, we created a time-optimizing motion planner that incorporated dynamics and degrees of freedom to transport objects really fast. However, in some cases, we found that it was possible to move too fast, causing contents to spill. So this led us to put an early stop to our rushing sommelier problem. We formulated constraints so that inertial forces would keep the contents in the container throughout the motion. With these constraints, the arm can rapidly transport open-top containers without spilling. When the cup is less full, we can relax the constraints and move the arm even faster. This robot can now do fast transport of a filled open-top wine glass without spilling a drop, thus addressing the rushing sommelier problem. Please come to our poster to learn more. Thanks.
Hi, I'm Ashvin, and in this work, we explore how robots can utilize prior data to learn skills in a new environment in a self-supervised way by setting goals and trying to achieve them. We begin with a prior data set of demonstrated behaviors, such as picking up objects, putting a lid on a pot, and opening and closing drawers with a lot of object diversity. And then the robot is dropped in a new environment. On the top left, you see that there's an unseen lid that the robot has never seen before. And now at training time, the robot has to practice potential tasks that the environment affords so that at test time, when the robot is tasked with a particular goal image, it can successfully achieve it. So to do so, we extract three things from the prior data. We extract a representation space, an affordance model, which predicts possible outcomes of an initial state. And then we also extract a goal condition policy or behavior model from the prior data using offline RL. Then, when the robot's dropped in a new environment, we use the affordance model to sample goals and then practice. In our results, we're able to learn several tasks this way, starting from offline initialization and improving significantly with online fine-tuning. Only about 5 minutes of robot interaction time. Additionally, we've released our algorithm code and experiments publicly. Please come to our poster to see more. Thank you.
Hello, my name is Wang Gyung-do, and I'm a PhD student at Stanford, working with Professor Mueller Kennedy. So I want to introduce our new tactile sensor DanceTech, which is a vision-based soft-tactile sensor that is capable of reconstructing surface deformation with high resolution and high accuracy. So DanceTech has a new hemispherical shape with a very soft elastomeric gel with reflective surface, while the camera is installed inside of the sensor. So we also proposed our new calibration process for the sensor and the adapted neural network to estimate the sensor surface from entire sensor image. So if you want to see further details about our sensor, please come to and visit the poster session. Thank you.
Hello, everyone. My name is Shivani. I work at Stanford with Professor Monroe Kennedy as well. And I'm here to talk about two directions that we've been working in. One is thinking about upper limb prosthesis as, in general, robots that augment human capabilities and the goals that they need to achieve, like being transparent like a traditional tool, but also having good levels of performance like an autonomous robot. And to test these concepts and to develop new methods of control, we're making a virtual platform in augmented reality. So the hope is that this would help to both study in neuroscience what happens in the brain when someone with limb loss thinks about moving their arm, and also provide a way to prototype and test new methods of controlling prosthesis. So I'm very happy to discuss at the poster if anyone's interested. Thank you.
Hey, good morning, everyone. So my name's Stephen James. I'm a postdoc with Peter Beal. I've just started. And we've got a lot of exciting projects going on, but here's just one of them. So basically, we're trying to improve course-defined queue attention. What is course-defined queue attention? Well, it allows us a way to kind of get a near lossless discretization of the translation space, which is normally unbounded, which means that we can use discrete action reinforcement learning algorithms. So the kind of output of this algorithm is the next best pose, and then we use a motion planner to get there. And this enables really efficient robot manipulation and can learn many tasks in the real world in a matter of minutes. And this is from high-resolution RGBD images. So what's wrong with it at the moment? So at the moment, it uses path planning, which is great from going from A to B. But if we want to do very particular trajectories, like opening a toilet seat, we need to learn from the demonstrations. And so how are we improving it? It's a very simple solution. We're just going to generate loads and loads and loads of trajectories and then rank them with a learned queue function, which is learned from the demos. And then this allows us to learn a distribution of these trajectories and maintain the sample efficiency. Thank you.
Hi everyone. My name is Feng Yu. I'm a PhD student working with Professor Alex Payan at UC Berkeley. Today we're going to propose a memory-based model predictive control. We all know that MPC is a powerful method in robotic application, but the major drawback of MPC is that the computational cost of MPC is too high. To alleviate the problem, we propose a hybrid control scheme that composes a neural network, a linear quadratic regulator, and a model predictor control. We show that through set control argument that you can prove that the hybrid control method is provably stable. You can also show that it's empirically efficient. We verify through a numerical experiment that our technique is highly efficient compared to an MPC in 4 applications, including the pendulum, triple pendulum, bicopter, and quadcopter. Happy to talk about the method in details during the poster session. Thank you.
Hi, my name is Keiko, and I work in the Multi-Robot Systems Lab at Stanford. So in my research, I've been working on methods for planning and control for autonomous drone racing, specifically where a quadrotor wants to race through a racetrack quickly. So our current approach to solving this problem is first approximating the quadrotor as a lower dimensional system and using Hamilton-Jacobi optimal control techniques to gain an initial policy. Using that policy, we then train a neural network for fast control updates and then use reinforcement learning with the full quadrotor dynamics to further improve that policy. On the bottom, you can see our approach working in the AirSim simulation environment. Feel free to come talk to me later. Thanks.
Great. Hi, everyone. My name is Joe, also with the Multi-Robot Systems Lab. And today I'll be talking about exact analysis for neural networks. And so what we focus on is neural networks with the ReLU activation. And these are known to be piecewise affine functions. And with that, we borrow a lot of analysis techniques from control theory. So we're able to compute exact forward and backward reachable sets. And we're able to find regions of attraction and certify local stability. And how we do this is this incremental conversion from the neural network equation to the piecewise affine form of polytope domain and affine function. And so this allows us to also certify safety properties, such as in traditional neural network verification problems. Finding unsafe inputs is a backward reachability problem. And with the region of attraction, we get about a factor of 80 speed up if we can certify the neural network is a homeomorphism. And I'm happy to talk more about all that at the poster session. Thank you.
Hi, everyone. My name is Fernando Castañeda, and I work with Professor Kosel Srinath at Berkeley. And this work is titled Gaussian Process-Based Safety Critical Control Under Model Uncertainty. And in our problem setting, we assume that we have access to a nominal model of the dynamics of the system that might be different from the true plant. And we want to design safe stabilizing controllers for the true system using control Lyapunov functions and control barrier functions. But the problem is that if we don't know correctly the dynamics of the system, we can't compute the CLF and CBF conditions because the derivatives depend on the dynamics of the system. So what we're going to do is fit the model uncertainty in these derivatives using Gaussian process regression and noting that the uncertainty is affine in the control input. We use Gaussian process upper confidence bound analysis to build chance constraints that can be incorporated in a min-norm optimization problem that is convex if we exploit the affine nature of the dynamics of the system. We also build feasibility arguments that give a good insight on whether the available data is sufficient to guarantee safety. Thank you very much.
Hi everyone, I'm Jun Wu from Berkeley. I'm going to present our recent work on the autonomous navigation of a biped robot Cassie. So in this work, robot can its own using a depth camera to perceive the world and the 3 layers of planners and variable walking height controllers to avoid to explore unknown environment with height constraints such as arch in this scenario. The robot is not only able to walk around ground obstacles but to crouch down to avoid collision with overhanging obstacles. In this work, we are the first to present an end-to-end autonomous navigation framework from vision all the way down to the motor talks for bipedal robot in height-constrained environments. Just give a goal locations, no preview map, robot can just walk to there by itself. Behind this, we develop a new reduced model and optimization trajectory planners to ensure the dynamic feasibility, safety, and gate stability for Cassie online. So we demonstrate the considerable autonomy of Cassie to explore various kind of unknown confined environments without a single for-all collisions. All right, thank you.
All right. So that was the end of the student spotlight session. I think we all ignored Mark's no clapping rule anyway, but I thought those were fantastic talks. If we could get one large round of applause. All right, and I think now we have our coffee break, and all of the students who just spoke have a poster set up outside, so feel free to get up and move around. Thanks.
Okay, so we have our next session. So this is the next set of faculty talks that you're going to have. There are 5 faculty talks starting from now till 11:45. And then at the very end, we are going to have only one spotlight talk. This is going to be Ambi Robotics. Our gold sponsors, they're going to give a talk at the end of the first set of faculty talks right now. So our first speaker is going to be Janette B. So really excited to have you, Janette. And you can start.
Thank you, Dorsa. So good morning, everyone. How's everyone feeling at this first in-person event in Mont? Yeah, I think we're all excited. Great. So my name is Janette B. I'm from the Interactive Perception and Robot Learning Lab. And overall, my research is driven by the question of why humans are so incredible at manipulation tasks. And it's really fairly unclear what the underlying principles are of this robustness, both in execution and learning. And it's even more unclear how to bring these principles to robots that have a completely different embodiment. So what's the goal of a manipulation robot? Well, it gets some sensory information, let's say pixels, and it needs to decide through some policy, for example, every millisecond, what kind of torques to send to the motors, right, to, for example, have the robot reach this drill. And of course, once it has moved, that changes completely what it perceives. And so it has to decide, based on this new information, what it's going to do next within a millisecond. And sometimes you even want to look ahead much longer than just a millisecond. You have to do some planning. OK, and in grasping manipulation, all this happens through contact interaction. OK, so let's admit planning for right now. Why, again, is robot manipulation so hard? Well, let's look at this robot. This robot has 25 joints. And let's assume it can only move, it has 3 discrete actions, like forward, backward, and 0 for each of these joints. And so there's a combination of 3 to the power of 24, so like 10 to the power of 11 different actions from which it can choose every millisecond, right? And so, of course, the motor torques are actually continuously valued, so infinite. So it's like a massive search problem. And now remember, we want to do planning and even plan over an entire time horizon. OK, so how do we do that? I think to make the search actually manageable, we need some kind of bias or some kind of structure to focus learning and optimization of good manipulation action into a good area of this vast space of possibilities. And of course, the million-dollar question is, how do you do that? And some of the approaches at IPRL that we are looking at are, for example, differential algorithms, renderers, physics models, and simulators that help us to put some structure into the learning process. We also are really interested in having robots learn from demonstration by just watching people, because that's kind of a relatively cheap way to teach robots, but comes with its own challenges. And we're exploring a lot of multiple modalities and using these for self-supervision in robotics. And so you've seen, we had 3 posters here at BARS. One by Rika Antonova, who focuses on active learning for deformable objects. One by Negin, who focuses on hand-object interaction and, for example, for VR applications. And one by Toki, who is focusing on grounding predicates through actions and combines learning with symbolic reasoning. So if you haven't had a chance to talk to them, go find them. They touch on all of these aspects that we are looking at IPRL. So I also want to make a quick plug for a new paper that just dropped yesterday on arXiv. So I've been actually involved together with others, also here at Stanford, in writing white papers, for example, with Dorsa, who's sitting here. In this case, on the challenges and opportunities for embodied intelligence. And you see there's some quite interesting co-authors on this. And this whole white paper came together from summer 2019 in Montreal, where we sat together in a room for 2 days or 3 days, I don't even remember, and looked at all of these aspects of robotics and learning. So feel free to look at this paper, and I would love to hear your thoughts. And of course, we also wrote this other white paper on the opportunities and risks of foundation models with all these authors. It's very broad. It's not just robotics. But there is a robotics section in it that we would love to hear your opinions on. I know Jitendra, sitting over here, has given his opinion, but I would love to hear many more from you. Thank you, Jitendra. OK, so with that, I just want to use the remaining time for a little bit of talking a little bit about a research project, actually together with Max Schwager. And there we looked at vision-only robot navigation in the neural radiance world. So recent work suggests promise in representing 3D environments as neural networks. And these networks take XYZ coordinates as input and return various properties at that location. So for example, by querying along a camera array, an image can be rendered in a fully differentiable manner. And although many works discuss training such network, and there are lots of advances right now in this direction, few discuss how they can be actually used in robotics. So we show how a trained nerve network can be used as a collision loss function to guide a gradient descent planner to find a dynamically feasible collision-free trajectory. The process is aware of the robot's dynamics, body shape, and orientation. And here's just another visualization of how this looks like for this optimization process, where on the right you see a plot that overlaps ground truth collisions with the collision as predicted by the nerve. And you see there's actually quite a good overlap. Also, we demonstrate most of this work on a quadrotor, but it will work on any system with differentiably flat dynamics, like this really useful robot here that is an omnidirectional couch. And what is cool is that this planner is also aware of these very intricate scene details, like flying through this gate here. And keep in mind, we assume, or what is cool about this is that we assume the robot only has an RGB camera to navigate through the world. And in this project, we also show how the RGB-only nerve renderings can be used as a measurement model to estimate the current pose and velocities of the robot using an EKF-like filter. So we combine the state estimator and trajectory optimizer into a controller capable of localizing and dynamically re-optimizing the trajectory to reject noise and disturbances such as wind. We combine the state at, so here's this example with actually using wind. And you can see it can still fly through the Stonehenge gate. Okay, so this was a quick sneak peek on this particular paper together with Max Raber, who can't be here today. And thank you so much for your attention. And I thank all my amazing students and my funding sources.
All right. So we have a question over there.
The next.
I think it's just on.
Yeah. Thanks for your great talk. But sometimes like human eyes also can get confused about like illusions or something. And then could your vision-based approach can compensate for them?
For illusions?
Yeah. So sometimes like when we make some decisions with only vision, sometimes we can get confused. So yeah.
That's a good point. So we haven't considered this case here. We are basically using rendered views, and I don't think illusions are really captured in here. So I can't really tell how it would react. One good thing about this work is that it's really closed loop. So it really does react to any new information it gets after it moved and could potentially adjust to that.
Thank you.
Yeah.
Okay. Any other questions? I can ask a kind of a philosophical one. So you mentioned multimodality and in general inductive biases, and there are different forms of multimodal data that we can really tap into. But I was wondering what your thoughts are on different types that are more useful or less useful than others. So I know you've looked at like audio, you've also looked at video, other sources, and in language. Any insights on
all of them? Yes, audio, touch, vision, depth, language, all of them. And yeah, and I would say that's kind of one of the questions we're looking into. When is what modality actually useful in what tasks? And I would say touch is specifically useful for manipulation tasks, maybe not for autonomous driving tasks so much, but yeah, so it really depends on the task, I would say. And we also have some work on actually learning what is important from these different modalities automatically. Which is interesting.
Okay.
Thank you.
Thank you, Janette. Okay. All right. So next we have Ricardo Sano from UC Santa Cruz here giving a talk. All right.
Thank you so much, Dorsa and Mark, for organizing this great event. It's great to be back in person. And today I'll be talking about something a little different than last time, talking about how to, one way to close the loop with physics and algorithms. We probably are all familiar with this paradigm where you have your specifications, your platform, your dream algorithm, you synthesize it, you test in simulation, you implement it, and then you hit a reality gap, right? There is no real algorithm that's going to work right away, so you need to iterate and optimize and go back and reiterate and optimize. And as I was telling my students on the way here, it's like similar to papers, right? We know that papers are never done. We are done with papers, and the same way we are done with algorithms, and we think that this is working, and we go and deploy it. The problem is that when we have a failure, then this whole thing restarts, and maybe you need to rethink about the whole procedure. And we know that fabrication plays a key role of this. The physics of the system play a key role. You have here a very expensive, tedious, complex process. Here you have a very local system that you want to design, and you want it to last for pretty much forever, right? And if you do a pretty lousy job, then you can probably hit situations like this, where you see that the bridge becomes a little bit of a jelly kind of thing, and you don't want to be having to drive your self-driving vehicle over that. The vehicle will get actually better as time goes. One of the things that we come up here is ways to use new technology to fabricate these systems in a way that we can now close the loop with fabrication as one of the systems. So how do we do this? Well, we're motivated by all these technologies, typically a small scale that you can actually build, code, simulate, and run, and solve very important problems, as you see right here, with technology. So I wanted to show you today some of the progress on this project, where we actually have a probable, correct, closed-loop system where the fabrication is in the loop. This is work with my colleagues, Michael Wenner, who is an expert on prototyping and uses Anna Cruz, Daniele Venturi, who is an expert on uncertainty quantification, and Shai Repsen at the University of Michigan, who is bio-inspired robotics. So what are we up to here? We are trying to come up with a way that we can design the algorithm for the physics, and the same way the physics for the algorithm. In other words, co-design. Okay? The idea is, what do we do here? We have multiple ways to go about this, and again, the traditional design doesn't really work because it takes forever. So here's the loop, here's the idea. We give a number of specifications, that's our initial design. We go in 3D rendering and graphical digital design. We print it, in this case, we prototype it, we test it, and as soon as we test it, we actually analyze whether this is a good design, and then we go back and regenerate a new system. So the loop involves not only the design of the system, but also design the algorithm, the testing, and then the validation, and then you close the loop. And that's where learning comes into play, as Janette was saying. You need to have a good estimator of your variables. You need to figure out a way how to do that. And that's what we use neural networks for. We need to also use optimization, not only of the algorithm, but also of the physics, right? So again, these are those knobs for us. We've been playing with a number of systems. Here are some of the systems that we have been playing. Drones, Crazy Fly, in-house generated snake bots, simple balls that you can essentially 3D print in minutes and then test for properties, and then the interconnection of them, like balls thrown at quadrators and the other way around. So I have a few minutes here. I'd like to tell you a little bit of it. I don't know how much time I have. At least 1 minute. Great. So design parameters, how do you build those? Well, a lot of digital design, CAD design, build the system. We came up with a tool that you can actually play with the physics, change it in real time with commands, and then create your 3D printed system. We test it. How do we test it? Well, first you need to assemble it. So there's quite a bit of interconnection between physics and computing, and many of you know about this. It needs to be rapid, it needs to be precise, and it needs to be following the specs. We build these systems, and then we test them. For testing, we do 3D reconstruction indoors for now. This could go outdoors. The standard control technologies can be suitable, but sometimes we need to redesign these learning schemes for attitude control, in particular, parameter identification. You see right here is an experiment of one of our systems where we have the algorithm running. This is a drone that we acquired from ST. The drone flies up, we collect data, and in real time we are assessing, is this the right physical design? Is this the right controller? And if that is not the case, we redesign, we print a new one, we put it in the camera system, and then we run it. So that's the vision of testing and redesign. Observers are tough. You need to estimate variables with very limited information. How do we do that? With noise, with uncertainty in the knowledge of the model. Multiple ways to do that. We essentially run a bank of estimators that we can use in order to determine which estimator is the best, which observer is the best for the state of the system. Kalman filter, you heard about this, optimization-based schemes, parameter ID, and we have tested this in all sorts of different systems. And we're very excited about this capability because it gives you essentially a plug-in-play way to test your systems. So I'm going to skip some of these details, but one of the things that are potentially very excited about to show you is that we can design balls, like you see right here, with different parameters, with different properties, and test them rapidly, and we can do the same for drones in the near future. And with that, I would like to thank the team members and everybody who put a lot of work on this. It's an Air Force research project for 2 years, and well, if anyone is interested, happy to tell you more during the breaks. Thanks.
So questions for Ricardo?
Yeah, I had a quick question about transfer of scale. So you started with examples of bridges, and you want to easily prototype these smaller scale systems. Have you looked at cases where the thing that you're actually interested in is a lot bigger?
Right.
Tested on how you transfer your learned parameters, or so to speak, to the bigger system.
Right. So the idea now is at the hobbyist, small scale level, but the concept will apply for larger systems. Certainly it won't work for an aircraft, right? Because it's way too expensive to actually test that. But for simple parts or subcomponents of the system, this is something that we're very excited about to apply to many problems: robotic manipulation, ground vehicles, you name it.
Right, I have one more question. So when you're looking at these types of problems, so you start with a specification. I was wondering how difficult it is to write that specification in practice. Like in practice, is it easy to actually get the system fully, or does it require some rounds of recurve, like even on this specification?
The specifications, as you know, they're typically a negotiable kind of object, right? The high level specification is I want to go from point A to point B is typically what is given. But in between is something that typically the engineers need to get into the picture and say, look, what you're telling me can be accomplished with as much battery, this much weight. So there's a lot of flexibility. So at this point, we are in very controlled theoretical level specifications, where it's very punctual, very concrete what we want to do. But you can essentially play with those specifications and come up with a totally different system. One question that I ask, if you change the specification a little bit, should the quadrotor have 4 propellers or should have 8 propellers? Should they be all on the same plane or should they have different angles? So that's essentially the idea, that the tool that we develop should be able to issue is a different type of system physically embodied, depending on the specification that you're given and based on the optimization that you run.
So currently it is given, but you could potentially like change that.
You can.
If needed. All right. Thank you, Ricardo. All right. So next you have Chelsea Finn from Stanford.
Hi, everyone. I'm fascinated by the problem of how robots might learn how to develop broadly intelligent behavior by interacting with their environment through algorithms like reinforcement learning. And for example, we've developed reinforcement learning algorithms that can use 2 to 3 hours of experience in order to learn a skill like this, where they insert a block into the shape sorting cube. And of course, typically, when we develop reinforcement learning algorithms, we don't just want them to learn one thing, we want them to learn many different things. And so what we often do is we wipe the robot's memory, then we run 2 to 3 hours more of reinforcement learning to train the robot to do a different task, like screwing a cap onto a bottle. And while it seems sensible to have reinforcement learning algorithms learn from scratch from their experience, from this standpoint, when we want to learn many different skills, it seems quite silly to have the robot wipe its memory after every previous thing that it's learned. And unfortunately, a lot of modern machine learning algorithms learn entirely from scratch, where they are essentially wiping their memory at the start of learning. So what I'm really interested in is, can the robot actually leverage its previous experience in order to more quickly solve a new task? Of course, this idea isn't really anything new. Almost 30 years ago, Sebastian Thrun was talking about lifelong robot learning and how robots can continuously learn and improve. Yet, a lot of our reinforcement learning algorithms are still operating in the setting where we're learning from scratch. So why is it hard to reuse previous experience? When we're using previous experience, we need to understand what the robot should be transferring from its previous experience and also what it shouldn't be transferring. And in particular, I'm going to talk about this lifelong reinforcement learning problem where a robot wants to ultimately solve many different tasks, and it's going to be solving them sequentially. And in particular, rather than starting from scratch for each task, we're going to try to actually retain previous experiences from previous tasks and use this to more effectively learn new tasks. So as a concrete example, maybe we want the robot to learn a sequence of tasks like this, where it first learns to insert a marker, then to cap a bottle, then to insert a block, and then to insert a different shape of block, and then to insert a marker into a different hole. How can we actually go about allowing a robot to learn this sequence of tasks much more efficiently than learning each of them individually from scratch? So we're going to break up the learning of each task into two different phases. First, in the offline phase, we're going to restore the data that we have from previous tasks and pre-train a policy for the current task using that previous experience. Then we'll get an initialization of a policy that can do something sensible for the current task. And then we're going to try to improve that policy with online experience. Now, the second stage is actually important, is a little bit tricky because we need to figure out how to leverage our data from previous tasks in an effective way to kind of efficiently improve with a little bit of online data. To study this step of the algorithm, we're going to try to reweigh our previous experiences, essentially trying to throw away past experiences that aren't relevant for the current task and especially keep experiences that are particularly relevant. We're going to use an equation that looks like this, where the second term simply corresponds to the ratio of the different data set sizes. So as we get more and more data for our target task, we are going to reweight our previous experience less. And then this first term is going to try to tell us whether or not the dynamics from our previous experiences is consistent with the dynamics for the current task. And we implement this with a thresholded weight based on this classifier C. And it turns out that you can actually estimate this, this ratio with a trick that uses just a binary classifier that's trained with a cross-entropy loss. And this is actually a trick that was used in previous work for a different kind of problem. OK, so we have these two phases, offline and online, and we use this to leverage previous experience when learning each new task. And this allows us to solve the problem that I mentioned before, where we first learn one task, and then we use the experience from that task when learning a new task, and we use this to solve a pretty long sequence of tasks, in this case, around 9 different tasks on a real robot. Quantitatively, we also evaluated the performance of this algorithm compared to learning from scratch for every task, which is really the de facto approach in reinforcement learning. And we found that this approach was able to learn about 2 times faster for each individual task compared to learning from scratch. And this graph right here is showing the learning progress averaged over all of the tasks. We're measuring the distance to the goal, so smaller is better. And we also find that the learning algorithm that leverages previous experiences is able to find a better solution than learning from scratch. So its final solution gets within 1 centimeter of the goal position, whereas learning from scratch only gets to 1.83 centimeters from the goal. So the takeaway here is that instead of learning from scratch for each task, robots should retain and leverage their previous experience. We also have some other works on trying to understand how we can aggregate previous experiences as well. There's probably lots of other diverse previous experiences that robots can leverage. And for example, we've talked about, we've looked into having robots collecting a lot of robot data and leveraging that to learn a new task in a new environment. And we've also looked at learning from broad videos of humans. And both of these works are presented as posters during the program today. I'd love to thank my students, and I'd especially like to highlight Annie Xia, who led the lifelong learning work that I presented. Thank you.
Okay, so we have a question.
Very interesting work, Chelsea. So I was wondering, sometimes when we move from task 1 to task 2, the reward doesn't transfer very well, because especially when we deal with ad hoc rewards that are very well defined in task 1, but they don't really mean anything in task 2. I noticed in one of your slides you had relabeled rewards. I was wondering if it refers to the same thing.
Yeah, so because the rewards can transfer across tasks, or maybe different actually for different tasks, what we do is we take the reward function for the new task, We get some sort of functional form of it, either we know it or we learn it, and then we use that to relabel our previous experience in order to leverage that previous experience with the new task. And so that's one thing that we find to be helpful. Of course, the dynamics may also change, and that's why we need that the classifier to determine whether or not the previous experience has consistent dynamics.
So I have one question about the like maybe a further optimization that could be done. So I think the way you pose the problem, we want to learn n tasks in sequence. Do you think it's possible to maybe optimize the ordering of the tasks to have good policies for all n tasks at the end? And do you think it's possible to maybe use demonstrations in addition to your likelihood weighting observation as well to do this?
Yeah, absolutely. So it certainly makes sense to have more of a curriculum of tasks. And actually, we had a task 0 that was actually just to reach a position, which is a lot easier than inserting something. And we found that to be helpful in a lot of the later tasks. You actually have to insert a little bit further in. So we already did that to some extent, but you could certainly exaggerate that much more. And then with respect to using demonstrations, yeah, I think that you could certainly incorporate demonstrations into the framework as well. And the bridge data set that I showed on the last slide actually is a data set of demonstrations, and we could use that sort of previous experience. We could also use it in the online improvement stage as well.
Got it. Thank you.
All right. Thank you, Chelsea. Okay, next we have Ken Goldberg from UC Berkeley.
Okay, thank you, Dorsa. And
the ARM lab in our focus. So I'm the director of the Assistive Robotics and Manipulation Lab. Our goal is to develop intelligent, assistive, collaborative robots that improve human life. And we look at this in three main areas. Robotic assistants, these are robots that might work alongside a person, intelligent wearables, and connected devices. So the kind of thread that runs through all of our work is really thinking about how a robot has to be able to model itself, a complex, possibly sequential task, as well as another entity, and likely a human, that it has to collaborate with. I'm very fortunate to have many amazing members in my group, but due to the limited time today, I'm only going to focus on two of their work. And we're going to look at this really thinking about the problem, why is human-robot collaboration valuable? So many scenarios that that come to mind, from minimizing risk to first responders, providing increased autonomy through assistance, as well as providing superior strength and stamina, and minimizing risk to human collaborators. So when we really think about what the barriers are here, we identified two main areas that some are on the end of low-level things that need to be developed, such as increasing the capability, such as dexterity. And then you have questions you need to ask on the side of collaboration, right? How do you have these robotic agents work effectively with human counterparts? So looking at the dexterous side first, if we think about the main challenge, the limiting thing that's keeping robots from operating autonomously inside of our homes beyond, let's say, a Roomba, I would actually draw one of the primary things down to dexterous manipulation. Same thing on the manufacturing standpoint. If you want to quickly assemble a small phone, because the technology is evolving very quickly, the main challenge is how do you correctly manipulate very small objects, and how do you have that confidence that a person does when they manipulate such objects? And when we zero in on this sort of problem here, we realize the role that the high density information our fingers are able to provide, including friction as well as shape, and that high resolution in order to be effective. And the shape as well of the fingertip, the design itself, plays a role in the types of tasks that you're able to complete. Here, for example, picking this coin up off of the table. So, this is where we want to be. This is a really cool video presented by OpenAI. This took many, many, many hours and even days and weeks to train how to do this type of manipulation. But when we look at for systems that we actually want to model that are able to actually reason about the tasks that they're doing and have that sensory feedback information, we see that there are a lot of tools in place, such as this sensor being gel site, that provide information about that surface that we're in contact. So what has been done, right? So we have, in this space of tactile manipulation, sensors that give a lot of information about pressure contacts. We have amazing strides in terms of gel site and digit. These fingers are a little bit flat, but they give you a lot of information and density at the contact. We have sensors like BubbleSoft, even OmniTac, that are all moving toward this new type of thinking for a robotic finger. But what's missing, right? What's the challenge here? I would put to you that while these sensors are at the top of the game in terms of giving you so much information, calibrating that information, and then learning how to modularize it so that you can learn quickly is the remaining challenge. So the work that we're looking at looks at three main factors here: design, modeling, and motion planning in order to accomplish this. Our student Wang Du presented earlier the sensor that we've been developing, DenseTac, where, similar to other sensors, it's a camera that is able to observe the interior deflection of a sensor, but what makes our approach different is how we calibrate in order to get super high resolution that's also accurate and we can use for modular models in the future. So I'm going to jump to the end of this video here and just show its ability to actually sense an object that we're actually able to sense here. So here you have a screw being pushed into our sensor. On the top left here, you see the raw image, you see a radial depth map, and then you'll see a point cloud of the sensor. And this is for the shape reconstruction side. And we're able to get, for over 30,000 images, less than 300 microns in accuracy for that contact surface. And so from there, we have this ability to sense shape at really high resolution, but you need force, like we talked about the slippage and how do you model the finger, model the contact in your finger. So here we lead to techniques on how we can increase that resolution and calibrate these forces at this super high resolution, and we also have to apply these methods of calibration in that regard as well. And once you have that, you can think about using these in tools such as wrench cone identification for your system. So on the collaborative robotics side, we have work that's really looking at how possibly you can actually have a prosthetic, a virtual prosthetic that the person is able to wear and is able to interpret what the person wants to do. This is really good for people who have that shoulder disarticulation. And so we're starting in simulation in order to understand how a person can actually communicate their high-level intent to a robot in order to perform these actions. And this plays a really big role in being able to predict what a person wants to do conditioned on the task that they're thinking about. What's really great is we can leverage that information about the context of the task as well as train the person as well. My last thing I'll mention here is Black in Robotics. It's a new organization that we developed whose goal is to actually increase diversity, inclusion, and equity in robotics. If you have more questions, we have a table in the back. Thank you very much.
All right, questions for Mondra?
Professor, I had a question on the combination of like, so you've shown that for collaborative robots, for assisted devices, you can use the haptic feedback. I wonder if you can also do that for robot and human collaboration, like manipulating the same object or, yeah.
Right, so you talk about like the dexterous manipulation, how could that play a role when you're actually interacting with a person?
Yeah.
Absolutely, right? And you know, I think it's an enabling technology, right? As soon as our robots are able to know more about how they're manipulating objects, that's going to play a big role in their ability to do things autonomously as well as their ability to collaborate. So absolutely.
All right. Okay, thank you, Monroe. So next, this is our last talk of this session. So this is a spotlight talk from Ambi Robotics.
Thank you, Dorsa. It's great to be here. Last time I was at the BARS event was 3 years ago, I think, and at that time I was on the other side of the table, so to speak, as a participant working in Ken Goldberg's lab. And I see a lot of familiar faces from my time back then, and it's really exciting to be back now representing the gold sponsor for this event. And you might ask, how did that happen? Well, I've been lucky to work with a lot of great people at Ambi Robotics now, coming out of the Auto Lab and continuing to grow since then, working on some incredible applications of the tech that we were developing at the university, specifically around simulation to reality transfer learning, modular hardware, and in-hand robotic dexterity. And we're really excited about trying to take that further and apply it to real-world problems that we see out there. These systems are in the field, working with people day in and day out. They're designed to work around people and to have people count on them every single day. So that's just thrilling to me to have that core technology that we had researched back at the University of California, Berkeley, become something very real and become something that people count on every day to have progress in the field. And this is a big problem. Over 50 million parcels are delivered every single day. And we're not only focused on parcels, but that's a big part of where we're pushing. So a little bit about the company. We're still relatively small, and that's by design. Everybody at Ambi matters a lot to our success. So it's really exciting to work with like-minded people who are vibrant and passionate about what they do. And we hope that maybe some of you could come join us or talk to us about what we're doing, about what you're doing, and how we could collaborate perhaps in the future. As I mentioned before, we're manufacturing real robots that are going out into the field. So if you want to know more about that process, come talk to us. We're looking for a lot of roles right now. As I mentioned, we're growing rapidly. We're about 20 people now and looking to about triple in the next year, which is thrilling and exciting. So please visit us if you have any interest in working with us and find out more about what we do. If you have any interest about talking about starting companies based off of university research, come talk to us. I've got a lot of things to say about that. Follow us on LinkedIn and Twitter. My name is Steven. Good to be here with you all. Thank you.
All right. Thank you, Stephen. Okay, so now we have our lunch break. So before you leave, two things. One is students for poster session. Can you take your posters down? And the second group can start setting it up during the lunch break. The second thing is we are starting sharp at 1:15. So please be back at 1:15. We'll have our keynote talk then. Faculty can walk down the hall to Fisher Conference Room. It's tiring. Thank you. Okay, so this was for people to just get seated. Okay, so we are now at during our afternoon session. So what we are going to do is we are going to start with our keynote talks. So during this session, we're going to have 2 keynotes, one by Percy Liang, and then after that, we're going to hear from Reish. Immediately after that, we're going to have faculty talks again. So Mark will take over and then moderate that session, and we'll have spotlight talks and then coffee break. So this is just reminding you what the plan is. So if you have questions so keynotes are longer. So if you have questions, you can of course, go to the mic. I can also walk to you and bring you the mic if you need to. So after the keynotes, we're going to have a little bit of time for discussion and questions. Okay, so now as everyone is sitting, so I have the pleasure of introducing Percy Liang here. So Percy is an associate professor in the computer science department here at Stanford. He did his undergrad at MIT and his PhD at UC Berkeley. He's the director of Center for Research on Foundation Models. His research spans many different areas in machine learning and natural language processing, including thinking about robustness, interpretability, and in general reasoning. He's also a strong proponent of reproducibility. He's the creator of the CodaLab worksheets, so that's pretty exciting. And then he has won many awards. So he has the PKS Award, NSF Career, Sloan Fellowship, Microsoft Research Fellowship, and many Best Paper Awards at places like ICML and Colt and EMNLP. So with that, today, Percy is going to tell us about foundation models and why we should care about them and what are some benefits of them in the field of robotics. So really excited to have you here, Percy, with us. Let's welcome Percy.
All right, thank you, Dorsa, for that wonderful introduction. Thanks everyone for being here. I think this is the liveliest crowd I've given a talk to in recent memories, so it's super exciting. And it's always fun giving a talk to an audience that I normally don't see, so I definitely am honored and excited to be here. So today's talk is going to be on foundation models. I'm going to talk about how they've really kind of transformed the field of NLP, but also how they've transformed my own thinking. Because 5 years ago, I definitely would not have imagined standing up here and talking about foundation models, especially to a robotics audience. So this is also a kind of invitation to, challenge and try to engage in the discourse. And I hope we'll have a bit of time for Q&A in a bit. So if we kind of rewind back almost a decade, so for a long time, I was working on semantic parsing since about 2011 to about 2017. And so the task of semantic parsing is taking natural language sentences, converting them into some sort of a logical form or program, whatever you want to call it, so that it can be executed, in this case, against a database, and that can give you your answer. So this is one way to do question answering. And the nice thing is that it really is this closest thing I can think of to kind of actually understanding the meaning of a sentence. And you can ask all sorts of crazy questions because it's backed by kind of these execution semantics on a database. Now, we also done some work in it doesn't have to be question answering on a database. The general idea applies kind of in a more robotic setting where you have actions. They can be similarly mapped to some sort of, let's say, plan. And if you toss that over to the planner, I understand this is where a lot of the hard stuff is, so I'm gonna, that's just one arrow in this talk for now. Then hopefully you get a sequence of actions that actually produces the right behavior. So I was happily working on semantic parsing for a while, and then I attended ICML in Lille in 2015. I distinctly remember this deep learning workshop. And I distinctly remember one of the quotes from a panelist, Neil Lawrence. And just as a context, so at this time, computer vision had already been pretty much transformed by deep learning. And NLP was kind of at the edge a bit. For some, Seek paper was 2014. So some areas had been transformed. Semantic parsing had not. And then Neil said, kind of glibly, I think, NLP is kind of like a rabbit in the headlights waiting to be flattened by the deep learning steam train. And at that time, my reaction could be best maybe characterize it as a scoff. I was like, no way, come on. I'm working on the semantics. This is like really deep understanding, and there's no way you can just like pattern match a bunch of things and get good results. So later, the next year in 2016, we developed a squad question answering data set. This was meant to be kind of a challenge to deep learning. The data set itself we didn't think it was that hard, but we thought it was hard enough that it could keep people from claiming that they solved NLP for a little bit. But it took about maybe 3 years for the best systems to start surpassing kind of human level performance. We released the 2.0 version, but that didn't, and we really tried hard to make kind of hard examples, but that didn't go so well from the point of view of making data sets hard. It went really well for the point of view of getting good performance. We also tried harder things, like let's be really adversarial. So you can take passages and add distracting sentences at the end of them, and you can get them to break fairly easily. And systematically, this is back in 2017, we looked at a bunch of models which had been submitted to the leaderboard, and we saw that all the accuracies kind of plummet. So we were, a little patted ourselves on the back a little bit. But, the reality is that these systems actually work extremely well. If you go do a Google search, question answering, the same kind of NLP models are powering question answering systems. This stuff, really kind of works most of the time, I would say. So in 2019, it was, I think, a really big event for the field of NLP. So there was a model called BERT that came out of Google. I'll skip over details. It's a transformer using masked language modeling. But the basic, why it was so exciting is essentially this table, which looks incredibly boring. But NLP people, this is what excites them, I guess, sometimes. So you look at all these each of these is a kind of a standard benchmark that people have been pounding at for a long time in NLP. And along comes BERT, and we see that across the board, accuracy goes up, by a significant amount. And the percentage points maybe not that big in maybe in absolute, but trust me, this is like kind of a significant in the context. I should just give a little bit of context where BERT obviously didn't come from a vacuum. There was a long history of word vectors and representations at the beginning of 2010s, and then there were precursors, language models that were trained and shown to help performance. And then this kind of later generation, BERT and post-BERT, with GPT-2, Roberta, T5, BART, and so on, I think really kind of transformed the models to a point where now it's kind of inconceivable that you would build a state-of-the-art NLP system without any of these language models. So now if we go back to the adversarial evaluation, we see how do these language models, when adapted, work. So Roberta is basically BERT but trained on more data. This actually does quite well. I mean, it's not quite human level, but this is 82 is way better than 40s. So this got me kind of thinking like, well, we can evaluate critically and we can acknowledge that these systems make errors, but what are we actually doing to fix these without manually crafting something to fix this particular example? And by far, the only thing that I've seen that kind of addresses this problem in a general way are these language models. So that's when I started kind of really thinking, well, okay, maybe this is something here, should pay attention. So then GPT-3 came out. So GPT-3 is just a language model. There's not really, it's incredibly simple in a certain sense. It happens to just be a very large language model trained on 500 gigabytes of text. So it gets 175 billion parameters. And when GPT-3 came out, you could go on Twitter and can find all sorts of things that people had done with GPT-3. So here's a tweet that says, hey, I used it to write some SQL for me. And here you can actually have a dialogue with the GPT-3. Now, of course, these are tweets, not academic papers. But still, this has been kind of validated a little bit more rigorously, but it goes to show how just diverse of a set of things that GPT-3 could do. Here I was like spending half a decade kind of working on semantic parsing, which is basically converting natural language to programs, and then GPT-3, just language model, doesn't get state-of-the-art accuracy, but it does a passable job. And that's what GPT-3 is good for. It's doing a kind of passable job on a wide range of downstream tasks. But the thing that really, I think, got my attention with GPT-3 is this phenomenon called in-context learning. And normal learning, you take a model, you get some examples, you backprop through the model. In context learning, you put the examples into you just take these examples and you concatenate them into a string, and then you feed them the examples into GPT-3, and you can get GPT-3 to solve all sorts of different ad hoc tasks. And this is kind of surprising because GPT-3 wasn't trained to do in-context learning. This is something that just kind of emerged. And one thing to comment on is the role of scale in this. So GPT-3 was trained on 175 billion parameters, which is way, way, way larger than the previous models. If you look at BERT, it's basically a flat pancake over here. And the scale is actually important, right? It's not just for PR purposes. Well, half for PR, but half for real purposes. If you look at the accuracy of in-context learning, at 1.3 billion parameters, you'll conclude that basically it doesn't work. You try to do in-context learning, its accuracy doesn't move at all. It's only when you get to 175 billion parameters that it starts working. So somehow the scale here is important. Now, that's not to say that we need this scale for in-context learning in particular to work, because I'm sure there's much more efficient ways of trying to achieve this. But it just shows that you can't ignore scale, let's say. Okay, this slide is for Jitendra. So I want to emphasize that this phenomenon is not specifically about language models. So earlier this year, OpenAI released DALL-E, which is a model that takes text and can generate images of all sorts of kind of different variations. In the other direction, you have OpenAI again releasing a clip model, which can take images and generate text, or more importantly, kind of embed them in a semantically meaningful way. So this result, I think, is worth looking at. So if you look at ImageNet, the ImageNet ResNet 101 gets 76.2, not state of the art, but pretty good, I guess. And the zero-shot clip gets 76.2. So even though this model was trained on 1 million images, and this model was not trained on this very kind of expensive hand-annotated data set, but just trained on much broader images. But what's more is that if you look at all the other kind of test sets that people have tried, you see that image model just like plummets. It doesn't work well out of distribution, whereas the clip model kind of holds its own. And now, I mean, this is kind of intuitive because if you don't train on ImageNet, you can't really overfit ImageNet in a certain sense. So, a lot of my other research, besides working on language and semantic parsing, was on thinking about how to robustify machine learning. And again, this is where it's like all roads lead to Rome. It's like this seems like a really promising way of robustifying, machine learning. So, okay, so I'm going to offer a definition of sorts. So foundation models is this term that we came up with this year because we felt like it was important to describe this trend that was happening. And it took a bit of time to figure out what was the right definition, and this is, I guess, as best as we can, conjure. So a foundation model is a model that's trained on broad data, usually using self-supervision at scale. and can be adapted to a wide range of downstream tasks. Okay, so the thing I'm trying to highlight is that you're training one model that can be, and you kind of invest a lot of resources in training one model, and then it can be useful for a wide range of downstream tasks. Not 2, not 3, but like almost all natural tasks I think you can think of for a particular domain. So this is not to say that there's foundation model has to be like one for the entire universe. It's for, let's say, natural language, there's one. Maybe for vision, there's another. But also multimodal models are interesting in themselves too. So here's a picture that I think illustrates foundation models. And I think of foundation models importantly as not so much a technological shift, because these ideas of self-supervision, transfer learning have been around for a while, right? I think John LeCun and Jeff Hinton were thinking about these self-supervised ideas in the 90s. We know ImageNet pre-training has been a thing for at least a decade. But I think this newer generation of foundation models that is emerging from NLP, I think have some distinct characteristics. So I'll just try to explain them from the context of NLP. So NLP used to be the case that every sub-area, like question answering, translation, sentiment analysis, parsing, was its kind of separate sub-community in a way. They had their own data sets, their models, approaches, evaluation, and so on. And what foundation model says is that now you can have a single model that is actually useful for all these tasks. So you train once using some language modeling like objective, and then you can adapt to question answering, translation, sentiment, and parsing. So importantly, the reason we call it foundation model, not like AGI model or whatever, is that we don't think that this model itself is sufficient to solve the whole task. You still, in order to get the best performance, you have to adapt it, okay, fine-tune it to your question answering data set or your translation or sentiment. But the lift that you get from having the shared infrastructure is substantial. So I want to talk a little bit about how the foundation models kind of intersects with society in a way. So these models are, it seems like everyone and their dog is training a foundation model if you have enough resources. And that usually means if you're a big tech company or a well-funded startup. And furthermore, there's these models are deployed, right? So Google since 2019 has been using BERT in their web page search. Microsoft is rolling out, GPT-3 in their Office products. Facebook is using these models to do hate speech detection. So they're already kind of out there. And so it's interesting to think about, what are the kind of consequences of this. And just to point out some, rather, I think, alarming consequences. So we know that it's been well documented that these models have a lot of harmful biases and stereotypes. So this is a paper from Abid et al. From James Zhou's group at Stanford, where they showed how if you prompt a language model with this innocent string, like 2 Muslims walked into and then asked GPT to complete, you get some really kind of disturbing, text. And so this is showing that, well, these models are trained on internet text, which have these harmful biases. So if you just blindly train a model and then use them, you can definitely inherit all of these biases as well. There's another paper came out this year, which is on the risks of GPT-3 for disinformation. So disinformation, remember 2016, it's a kind of a problem. And I think one potential worry with these language models is that they actually can amplify, bad actors' ability to do disinformation, because now you don't have to hire a native English speaker. You can actually just use the model, and these are, I think, GPT-3 I think costs maybe about $4 or $5 million to train. So this is, pretty affordable if you're a state government. And you can see that these are some tweets from this paper that is about climate change or denying climate change. And you could see how GPT, with its ability to kind of personalize different contexts, could create a lot of confusion if not dealt with properly. Another problem I want to mention with these models is that there's a loss in accessibility. So one of the things that I think is often overlooked in deep learning is that there's an incredible amount of openness with a culture. You see these data sets that you can just download, packages built on open source frameworks like PyTorch or TensorFlow that people can use, which enable all of us to kind of iterate and participate in research relating to deep learning. But foundation models is another story. Many of these models are not released. Maybe sometimes the code or the data set isn't even released. And this is kind of problematic from a point of view of reproducibility and open science. I should shout out to a few efforts that have been trying to fight against this. So Eleuther AI is this distributed organization that has released a number of resources like the data sets and trained initial models, all completely open. Hugging Face has this big science project that's trying to train a large model as well, kind of more in an open and open way. But it's tough, right? These still require tons of resources, and unless you're one of the big tech companies, it's very hard to be able to train these models. And I will say also, why is it important to train? Because all of these issues regarding biases and efficiency issues, I think are fundamental. You can't just take an off-the-shelf model. You can probe it, you can study it, but if you can't change it, which requires training, then you're kind of stuck in a sense. And it certainly limits the number of types of research questions you can ask. Okay, so with all this kind of motivation, let me talk a little bit about the Center for Research on Foundation Models, which we started this year at Stanford through HAI. So this is a community that I think evolved relatively organically in a bottom-up way. We realized that there were just a lot of people on campus who were interested in some aspect of foundation models, and we thought it would be a good idea if people who weren't normally talking were talking, essentially. So this has over 200 students, postdocs, faculty across 10 different departments. And one thing that we are trying to do, instead of beyond just getting people to talk to each other, which is obviously very productive, is we have a development team. Led by Sid, who I think is in the audience, and Laurel. And the goal here is to release open source tools, data sets, and models to make foundation models more accessible, because we think that this is important technology that we don't want to kind of become closed off. And by the way, we're also hiring a research engineer. So if you or your friends want to work on large-scale machine learning at a kind of interdisciplinary environment, please come talk to me. So the center is doing a lot of different research. Let me just briefly give you a taste of some of the questions that we're interested in. So on the more technical side, there's improving the efficiency of these architectures, trainings, and fine-tuning approaches, which is very natural. I think a lot of the mysteries of why these models are effective have to do with the data. And data is something that often gets overlooked. So we want to study the effect of data on models. And then finally, can we get a more rigorous theoretical understanding of why these foundation models work? This is a thing that I think bothers a lot of people. Well, it works empirically, but why? On the more kind of societal side, I think there's a number of interesting questions as well. So we have a project trying to understand the economic impact of using language models for writing and coding. What's the impact of disinformation, as I mentioned before, which is important. What are the ethical problems with homogenization? So we've been talking with Rob Reish, who's going to give the next talk on the ethics of foundation models and what happens when you have this kind of immense centralization that happens. And then finally, more longer term, can we reimagine the future ecosystem around foundation models, right? So the current practice of big companies scraping lots of data and training one gigantic model and having it relatively closed off is not an inevitable outcome. And I think it would be nice to have greater participation, greater modularity, and think about how people creating data can get value out of these processes rather than just having the data just end up in the big data set. And then finally, which is relevant for this workshop, how can foundation models transform robotics? So I'm asking this a little bit provocatively. And so if you look at NLP, vision, and robotics, one is kind of different than the other, and the other two. And I think one challenge with robotics has always been because you have to be in the physical world. It's much harder to scale up, things break. Whereas vision and NLP have the luxury of just using internet data to train models and get all these fancy results. So in this in the report that we put out this year, we had one chapter on robotics that Dorsa, Chelsea, and Janette wrote along with some students. And here is a picture. This is kind of a vision. This doesn't exist, but it's a vision of how one might think about it. So if you look at the data sources, you have robotic interactions, videos of humans, things that happen in simulation, maybe some natural language. One thing about foundation models I learned is that they're really good at synthesizing kind of different modalities and connecting different modalities. So can you somehow shove, for lack of a better word, that into a data set and train a foundation model, and then you would be able to adapt it to much of the kind of classic robotics pipeline, for example, specifying a task or specifying a policy and so on. So there's a bunch of questions here which we're actively thinking about, and I would welcome any discussion or on this topic. One particular thing I'm kind of interested in, just to be a little provocative, is how far can you get without actions, and how far can you get without interaction? So clearly, actions and interaction, there's a lot of evidence that show that they're important for an intelligent agent to behave in the world. So there's no doubt that they're necessary to get there, whatever there means. But the question is, how far can you get without them? And why do I want to ask this question? It's because there's a lot of data, which, in particular videos, which are not annotated with actions, or they're not even of robots. And it seems like if you can harness all of this data in some way, you can maybe make quite a big, a lot of progress. So the how far question, I don't know. I mean, is it this much? So in this pipeline, there's training and there's adaptation. So is it less than 50%, or is it more than 50%, whatever the scale is? But I will say that one important kind of lesson that I've from NLP is that it turns out that pre-training and fine-tuning, the task and the actual thing you care about, can be much farther apart than we think. If you think about the success of foundation models, you're predicting the next word. You could, a 5-year-old version of myself would have been very skeptical. Well, what does predicting the next word have to do with, solving semantic parsing? And, it's definitely has a lot of things which are relevant, but it turns out that predicting the next word gives you representations which are then helpful. It also gives you a lot of things which are, useless, but, you can't, maybe that doesn't bother you too much. So when kind of in the real world and in vision, things are much more complex, high dimensional and noisy perhaps, but I don't know what the right answer here is. So with that, I will open up for questions if we have time. I'd love to get people's thoughts on things. Thank you.
Thank you, Percy, for the great talk. So yeah, do we have any questions?
Yeah, do you have any opinions on what makes a good foundation model versus a task-specific model in terms of like architecture or the way it's trained? Is there something that makes a type of architecture better at this kind of generalization task than others?
Yeah, what kind of architectures make a good foundation model? Well, it seems like transformer architectures are the ones that have really, dominated in this foundation model space. Mostly because they just take advantage of the parallelism of the GPU much more effectively. They can model long-range dependencies and so on. But I don't think that this is somehow, transformers are not sacred. And I think there should be other alternatives, some of which we're exploring at Stanford as well. The other thing that you might wonder about is, in terms of scaling, transformers, because they're dense, they have limits. You can't have a transformer that over 1 billion tokens, and people have looked into, mixture of, expert style models, but the jury is out on whether that's, a productive route or not. Yeah.
Thank you for the talk, Percy. So 2 quick questions. In robotics, there's a big difference I would say, between question answering and robotics, which is in fault tolerance. So in robotics, a lot of cases, you really can't afford to have faults. And you just gave us a number of examples where the systems do fail, which isn't such a big deal if you're just answering questions. So I'm curious to what degree you're thinking about that. And also, since here we are at the home of Terry Winograd and the Winograd schemas, I'm just curious to what degree you're using those to test and probe these kind of models.
Yeah, so robustness, I think, is in a very important part. Even in language, I think it's important. If you imagine a chatbot that's doing like emotional support or something, you could imagine definitely things going pretty downhill from there. I would say that foundation models, there's this trade-off, right? Like you can use foundation models as a pre-training just to do classification in kind of a domain that you understand. For example, in text generation, you can say, I'm going to restrict myself to a grammar, a fixed grammar, so it can only generate these possibilities, and all I'm doing is selecting between them. And I think it will be productive there. Of course, that limits what you can do. So today, I think we can use foundation models in kind of these more limited ways. There's a lot of research to be done on how to make them more robust. And when they're more robust, maybe we kind of loosen the rope a little bit and allow them to do more. But I think I want to emphasize that the adaptation of a foundation model is really important. I think we tend to pick up on the foundation model because it's in the middle, and it is impressive and interesting, but the adaptation and how you harness the power is equally important for real applications.
Okay, so if I have another minute, so just let me just come back to the question I asked, which is the difference in robustness for robotics, because you made a claim that this is also foundational models are going to be essential for the future of robotics. So I think for our audience, we're wondering, in our world, you can't have that kind of fault tolerance. You're not very fault tolerant. To what degree do you think these foundational models will be fault tolerant?
Yeah, so it depends.
For robotics.
Yeah, so I think that you can think about, so the way I would want to think about this is there are places where perhaps, so if you think about, let's say, kind of understanding maybe a overloaded word, but let's say vision, recognizing objects in a scene. So that could be potentially pretty useful, if especially done in very kind of new environments. So you could say, well, maybe I don't want a foundation model that does control but I just want it to do some perception. So that would be one way of resolving. You wouldn't be able to get all the way there, not nearly all the way there, but you would get some benefit from that. I think that the more ambitious thing is to think about how foundation models, if you, for example, look at videos of things happening in the world and build a sense of what are likely trajectories and what are good and bad trajectories, maybe you can use that as a prior at least. So I think these are, meant to be kind of rough guides as opposed to here is the thing that we would trust. I don't know if that's...
Since we're talking about question answering, did that answer my question? No. But I do think it's really important because you obviously have been converted to the power of these models for natural language, but I think it's a big stretch to extend that back to robotics. So that's my question to you, and you've sort of said that is one of the areas that the foundational models are going to be useful, and I think the question is very much open.
Yeah.
Okay.
I'm happy to talk more offline.
All right.
About this.
Thank you.
Okay.
All right. Thank you, Percy. And yeah, let's thank Percy one more time.
Thank you.
Okay, so next we have our second keynote speech. So this is by Rob Reish. So Rob is a professor in political science at Stanford. He's the director of Center for Ethics and Society and co-director of the Center on Philanthropy and Civil Society. He's also the associate director of Stanford High Human-Centered AI Institute. Some of his newest works are kind of at the intersection of technology and ethics. So that's actually the topic that he's going to talk to us a little bit about today. He has 2 new books in 2021, so he has been very busy this past year. One is on digital technology and democratic theory, and the other one is on system error. Rob is the recipient of multiple teaching awards. And he has written several books on education. He's also written for New York Times, Washington Post, and The Wired. So really excited to have you here with us, Rob.
Thank you very much. All right. What is a philosopher doing at a robotics symposium? Well, it's true that although my background is as a philosopher, I've been doing some work over the past couple of years with people on campus here in the computer science department and engineering. You just heard about this new book that I co-authored with the most popular undergraduate teacher at Stanford. That's Mehran Zahami, the instructor for the CS106A, along with a social scientist or a policy expert, Jeremy Weinstein, who served at the highest levels of the Obama administration. So I'm going to draw a little bit of the talk I'm going to give you about ethics and the development of smart machines from some of the material in this class and from this book. And I want to speak as well, hopefully, to some questions about foundation models. I've been working with Percy. I have an interesting, perhaps alternative answer to the question that just came here about false positives and false negatives, but we'll get to that at the end. And I'll give you, in good old philosophical style, some provocations. I'm not here to pour my moral expertise into your brains. I'm here to illuminate moral complexity and invite you into conversation and dialogue about what I view as the inescapable ethical questions that arise doing technical work. So, a couple of years ago, there was this headline in the New York Times. We're now aware that technologists are no longer just hackers coding away in the garage. They've acquired great power in startups and Silicon Valley big tech companies. And there's a dark underside to various forms of big tech or just technology in general: algorithmic bias, privacy violations, misinformation, disinformation, amplified hate speech, automation that displaces human labor, and so on and so on. And so a variety of universities have tried various ways to integrate ethical questions, policy questions, and technical questions all in the same class. So I began teaching this class 4 years ago with Mehran and Jeremy. The idea was to bring 3 different frameworks into a single class, chiefly computer science students here. But the idea is you have to write a philosophy paper, you have to write a policy memo, and you have to do technical assignments all in the same class. Ethics is not a checkbox where you take one course and you're done with it, ready to go, but rather something you ought to encounter all along the way. Because as I say, my starting presupposition for you is that ethics is inevitable, inescapable. You must confront ethical questions, and the task is to avoid moral sleepwalking. Having the idea that you have a moral compass in your back pocket, that you're a good person and you no longer need to be awake to the moral complexity that confronts you as a technologist, seems to me a mistake to avoid. So let me begin with a quote that I take to heart. This is a lovely one. See if you know who said this. What the inventive genius of mankind has bestowed upon us in the last 100 years could have made human life carefree and happy if the development of the organizing power of man had been able to keep step with his technical advances. But as it is, the achievements of the machine age in the hands of our generation are as dangerous as a razor in the hands of a 3-year-old. Anybody know? Shout it out. Albert Einstein, almost 90 years ago, is the one who said that. Gives us a sense about how the extraordinary promise of technology to liberate human beings from various forms of misery and drudgery hasn't been accompanied by the organizing power of humankind to shepherd technology in an all things considered beneficial direction. It's also ushered in extraordinary danger and harm. So that's the premise of why I think thinking about ethics is necessary. You're all familiar with the language, I'm guessing, of dual-use technology, the idea that a hammer can be used for good and can be used for ill. The person who invented the hammer or designed the hammer can't be responsible, of course, for someone who takes the hammer and clubs another human over the head, as opposed to hammering a nail into a board. And so dual-use purposes is something that's familiar to us. And of course, it's appropriate that the developer of a particular tool or technology not bear responsibility for the different use cases to which those tools or technologies are put. However, what I want to suggest to you is that leaving aside that kind of question, the much more interesting questions are the ideas that it is inevitable that values are embedded into technologies themselves. You cannot help but to impart implicitly or explicitly a set of value choices into the development of technical tools. The easiest example I can offer you to illustrate this is something like on your phones right now, you probably have WhatsApp or Signal or iMessage, which are end-to-end encrypted messaging systems. Through this extraordinary technical achievement of encryption, that places a huge thumb on the scale of individual privacy. It is a technical achievement to try to guarantee user privacy at the expense of other potentially important values too, like personal safety or national security. So when the iPhone is used by the terrorists in the San Bernardino attack and the FBI now has the iPhone in its possession and wants to get a backdoor entry to it, Apple says no to the US government to investigate a terrorist crime. Or when Apple just recently wants to scan photos uploaded to iCloud to look for child pornography, there's an interesting question between guaranteeing privacy and guaranteeing personal safety or security. There are values embedded into technical choices and products. That's the basic premise of this. And what I want to suggest to you again is that you should be awake to these value choices, have arguments on behalf of the value choices you make, and then be prepared to defend them more broadly as people begin to use your tools and technologies more widely. All right. I'm going to give you next 3 different lenses or frameworks to think about ethics in the development of smart machines, and then we'll end with a short discussion, since as I promised at the start, ethics is chiefly about dialogue, not about one-way unidirectional learning. So 3 ethical lenses. I'm going to suggest to you that you can think of these questions through the lens of personal ethics, professional ethics, and then social or political ethics. Personal ethics is perhaps the most obvious one, that you should have a personal moral compass, that you should try to have an answer to the question, what makes a good or bad person or a good or bad technologist? Professional ethics organizes the collective enterprise of technologists, the kinds of things that bind us together, not necessarily through law, but through custom or habit or norm, about being a professional in good standing. And then finally, social or political ethics are those values across society. They invite questions of governance, of legitimacy. Now, I want to suggest to you that though personal ethics is, of course, important, it is the least interesting set of ethical questions to ask. Elizabeth Holmes, the famous dropout of Stanford, now accused of various crimes, standing trial. Well, is there anything ethically interesting about Elizabeth Holmes's failure, alleged failure as the founder of Theranos? This fake it till you'll make it culture, the idea that there's this unethical underside of Silicon Valley. Too many startups take a take it till you'll make it, fake it till you make it kind of orientation. I want to suggest that there's no good case to be made. There's no ethical argument on behalf of lying, cheating, deceiving, or stealing. So having interesting ethical debates about whether or not what Lewandowski did or Elizabeth Holmes did, not so interesting. What you probably need to know about these questions is that the interesting questions about personal ethics arise in whistleblowing. Here's the whistleblower from Theranos, who took extraordinary risk on his own back to leak the information from inside Theranos to a Wall Street Journal reporter, or of course, more recently, Frances Haugen with Facebook. So I want to suggest to you that we disregard for the moment personal ethics, because probably you either learned various things in kindergarten about not lying, cheating, and stealing, and an ethics course in university or an ethics tutorial in a company is not going to make a difference. Put it differently, we should not be interested in whether Mark Zuckerberg is a good or bad person, or Facebook is a good or bad company. We should ask questions about the systemic incentives of technology and tech companies, the system error that comes from the title of the book, not about good and bad people. So that gets us into professional ethics. That's where I think the more interesting action is. Professional ethics has to do with codes of conduct, institutional or organizational sanctions or norms. Now, here again, in the spirit of being provocative, you all probably know that computer science as a discipline dates back perhaps in the earliest of cases to 1950s. And the power of technologists in society is more recent than that. Artificial intelligence and its extraordinary advances into companies and into the products that so many of us now use raises a set of questions about professional ethics that I want to suggest to you could be usefully compared to the set of professional ethics that exist in older professions, like the law or medicine, where there are a richer set of norms and a more wide-ranging institutional footprint for the practice of the profession in good standing. So here is a comparison between a set of professional ethics in biomedical research as compared to computer science research. You've got the Hippocratic Oath in biomedical research. You've got professional licensure requirements. If you do something as a healthcare provider against your profession, you can have your license withdrawn and you can't practice anymore. You have an IRB if you have human subjects. You can't just start doing your experiment. You have to pass through a protocol that has ethics at the center of it. There are federal agencies here and in other countries that are responsible for overseeing the rollout of various drugs and experiments. And finally, there's a robust field of biomedical ethics. You have ethics committees at hospitals. There's an enormous footprint, an institutional footprint of professional norms. What is the comparison in computer science or in AI? Well, the ACM has a code of ethics, no enforcement mechanisms. Do you know anyone whose membership in ACM has been withdrawn for a violation of the code of ethics? There's no IRB equivalent. You can do your data science or A/B testing, whatever it turns out to be, without passing through any institutional review. No requirement of an ethics review of any experiments you undertake. And there's no regulatory body that governs the work of companies or AI scientists. Or to put it differently, think back a few years ago to that other super important technological revolution of the past decade, CRISPR, gene editing technique, in which a Chinese scientist used the CRISPR gene editing technique on a human baby. The professional scientific community immediately ostracized him from the respectable practice of biomedical science, disinvited from professional conferences, not able to publish in any journals. Can you think of an AI scientist who has been excommunicated from the practice of respectable AI science, who did something against the community's norms of what it means to be a good, professional, artificial intelligence expert, and who no longer can practice in good standing? I don't know an answer to that question, and if you do, I'd welcome hearing about it. Third and finally, professional ethics yields then questions about social and political ethics. This is the realm of value trade-offs and tensions in broader societal settings, in which we ask questions like, is it appropriate for Mark Zuckerberg to be the unilateral governor or dictator of the speech environment of nearly 4 billion people? How is Mark Zuckerberg entitled to referee the trade-off between freedom of expression on Facebook, trying to ward off hate speech, and then misinformation and disinformation and other kinds of problems? He makes decisions alone, ultimately, given the governance structure of Facebook, for things that affect an enormous community of people. There are value trade-offs. Mark Zuckerberg's value trade-offs become our trade-offs. And so social and political ethics invites us to think about the society-wide tensions in values. To put it in a simple way, here's one way a philosopher put it, one of the philosophers I like quite a bit, an English philosopher named Isaiah Berlin. Total liberty for the wolves is certain death to the lambs. We have a tension between liberty and equality. Or to put it in personal life rather than political life, you believe in always telling the truth no matter what. I do not, because telling the truth all the time, optimizing for the truth, can be dangerous. You wonder if that's true. If you ever go to a wedding and the bride or groom comes out and says, "How do I look?" you have only one answer to give them. If you're a truth teller then, you will lose your friendship. Okay, that's the sense of value trade-offs. Now, the end result of this is that I want all of us to be awakened to the necessity of confronting these value tensions, even in the development of technology from its very start, in the development of foundation models, in the development of any robotics application. We are not passive in the face of technological development. We have agency to shape our future. So I want to end by inviting you to a short dialogue. I'll take an example that perhaps is familiar to most of you with autonomous vehicles. Here's a graph of the significance of injury to people from roadway accidents, which is always in the top 10 of the highest causes of death or injury. And you see that there are pedestrians injured, passengers injured, motorcyclists injured, and that green bar on top is bicyclists. Now, you were thinking the philosopher is going to come and give the trolley problem as the interesting philosophical example. No, I'm going to disappoint you because you've probably heard that and done that already. If you don't know what it is, interesting. But what I want to do is ask you a different question about this. Obviously, there's extraordinary promise with autonomous vehicles, with these robotic devices on which humans can sit and ride, because humans are crappy drivers. And if autonomous vehicles can be better drivers than humans, we'll have enormous gains in human welfare. However, based on my initial research, maybe you know different, but based on my research from this class I've been teaching and now in this book, currently in the pilot testing of autonomous vehicles, they show great promise in protecting passenger lives, in protecting pedestrian lives, and in protecting motorcyclists. But the sensors have a difficult time identifying bicyclists, given the roadway infrastructure. So if you work for an autonomous vehicle company, or if you work in a public agency, or if you're an ordinary citizen thinking about your own transportation choices, what I want to ask you is, should we release autonomous vehicles in their form now with extraordinary benefits for a large part of the population? We're going to get a net benefit to pedestrians, passengers, and motorcyclists. However, given this, bicyclists are slightly worse off. If it's the case that bicyclists are slightly worse off with autonomous vehicles on the road, but we have a net gain, what should we do? Talk to the person next to you. I want to give you the following assumption when you do. Assume that the roadway infrastructure can't be changed right away. So your attempt to wriggle out by saying the government should fund bicycle lanes in a different place is not an opening answer. Talk to each other for a couple minutes. Take one more minute. All right. Let's do a quick poll. I could invite you to think of yourself as working within the AV company. You incredible technologist, developer of this extraordinary robot, a fleet of autonomous vehicles. You've succeeded in making something that improves human welfare overall, but at least in current technological frontier, bicyclists are slightly worse off. People are looking to you because you helped develop the technology in order for an answer to the question, should we roll it out now, even if bicyclists are slightly worse off? Raise your hand if you say we roll it out now and get the net gain, even though bicyclists are slightly worse off. All right. Raise your hand if you say, no, we wait until somehow the road infrastructure can be changed or the technology is good enough for all subpopulations. And there are a whole bunch of people then who aren't voting. Moral complexity, or you're saying, hey, there's more than just two choices here. Go ahead, you got a point. Go up to the microphone and give it. See, this is Socratic method at work.
I think there is another solution here.
Yeah.
The solution would be go for that, but then specify a specific funding to support researchers to focus on that specific solution.
Yep. Good. Get funding to give researchers the money to focus on a specific solution. Exactly. Right. More research is needed. The classic line of any scholar, any developer. I love it. I think that too. Philosophy, we need a bunch more money to look at these value tensions and trade-offs as well. All right. Now, of course, you'd say the solution is to fix the roadway infrastructure, to improve the sensors. There's a variety of ways to that. All right, let's say the sensor technology isn't good enough now. We can get big benefits right now if we release the cars. Well, who should pay for the roadway infrastructure changes? Should it be the AV companies who should be taxed now to pay for the infrastructure changes? Should it be all citizens? Should it be the bicyclists who should pay? That was actually proposed to me in a discussion about this. All right, you can see the ethical, social questions that arise. You'll be invited to have views about this wherever you happen to be in society. I'll end with one more example, a real-life example, not hypothetical. Well, neither is this one about bicyclists. If you're in charge of public policy for Uber, your engineering team making great progress, you're trying to figure out how to test your AVs. California has a lot of regulations. They impose a bunch of regulatory guardrails that slow down your testing and experimentation. The governor of Arizona, a guy named Doug Ducey, says, hey, Uber, come on over to Arizona. No rules here. Get testing whenever you want. We're happy to have you. Do you go to Arizona and accept Doug Ducey's invitation? Does it matter to you whether Doug Ducey offered this alone or whether he consulted with the legislature? How do you decide to act? Take 90 seconds for an answer from inside Uber, where I've just placed you. Talk with each other again. All right, you won't have resolved it all in that sort of amount of time. In order to keep to schedule, I'm going to refrain from asking you your view. I'll just say that the question should seem complicated. Well, maybe if California is overruling, the governor of Arizona is democratically elected, isn't he? He's a good enough representative of the people of Arizona to invite us in. We go someplace else. Or you might think, well, if he didn't consult with the legislature, What happens if in the next election the governor leaves and we get regulatory uncertainty? We go invest a whole bunch of time and talent and money in Arizona. A governor changes because the legislature hasn't bought into this. And now you get a different regulatory environment. What happened in actuality here? You probably know the answer. Uber went, piloted a whole bunch of autonomous vehicles in a mostly regulation-free environment. And one of the autonomous vehicles killed a pedestrian. And then ordinary citizens, when they saw autonomous vehicles on the road, started pelting them with rocks, attacking them like they were, you know, robots out to kill people, making trouble for the governor and the legislature, and of course for the company. All right, I hope I've been over dramatic a bit, but making my basic point, which is that you cannot escape confronting questions of this kind. There's no such thing as handing this off to someone else. Do not hire a chief ethics officer in a company. Horrible idea. There is no idea of outsourcing ethics to the expert as if it was legal compliance. You bear some responsibility for thinking through the ethical questions from the start of the design and development of the technology. And there is a zone here in which the answers register in better and worse, not right and wrong. I know that often makes engineers uncomfortable. They want the cleanliness of right and wrong, true or false. But in the realm of professional ethics and social and political ethics, mostly it's better and worse answers. Be prepared to offer your answers to value tensions. That's my invitation to you, in which I hope to be a part of it as someone with some philosophical training. And I'd love to hear more about your work. Do we have time for a question or two, or should we move along? As you wish.
Let's thank Robert. Right. Okay, so maybe we have time for one quick question if anyone has questions. And yeah, Jitendra.
Not a question, it's a comment.
Good.
I think that currently in computer vision, one of the big ones where this dilemma is being faced is research on deep fakes.
Yep.
So as researchers, we love developing techniques which can really produce these images which are as good as real. But of course, this is leading to lots of harm. And the question is, I personally believe that the computer vision community should stop doing research on deepfakes.
Yep.
Because right now there are two branches of the community, one doing research on creating deepfakes and the other trying to detect deepfakes. It's like the crypto business. But, and this is fun for people, but it's like developing biological warfare weapons.
Right.
Some things you should decide not to work on.
Thank you. Excellent.
All right, let's thank Rob and Percy again. So the faculty speakers for this session, it would be great to have you guys up front. I think some of you are further down, and I'm going to switch to Mark.
Thank you. Yeah, just want to make sure, Sergey, there you go, excellent. All right, Steve, we're going to move right to the faculty speakers. Steve's up first from Stanford. Go ahead, Steve.
And great talk, Bob. Very exciting, tough act to follow. So I'm Steve Collins, and I'm a professor here at Stanford. And in our group, we try to develop exoskeletons and prosthetic limbs to make walking easier, especially for people with disabilities. And this is a lot harder than it might seem at first. The popular image is that the problem here all has to do with fancy energy sources or clever mechanical design or just cost. And none of that is true. The real challenge in designing exoskeletons is that humans are incredibly complex, especially in our nervous systems. And this makes it very difficult to predict how a person will respond to some new device that we dream up and give them until we actually test with that person. And this has made progress very slow in our field. In the bad old days, what we do is dream up a device, build it, test it on people, and because we don't have a good model of people, the device would fail to benefit them. And this whole process would take years to evaluate one design idea. And then, of course, the student graduates, and we start all over from scratch. So my laboratory has been working on new approaches to make this empirical process faster. And one thing that we've developed are what we call emulators. These are hardware systems designed for versatility. so that you can think of this as sort of a virtual reality system for your legs. A person gets the physical experience of interacting with some new design without having to build it. And so we can cycle through new design ideas in days or even minutes rather than years. A second set of tools we developed are intended to search this vast space of potential assistance strategies faster. And we call this human-in-the-loop optimization. So what we do is we have a person put on an exoskeleton or prosthesis, and they'll walk or run, and the device will apply a pattern of assistance and will measure their actual performance with that assistance in real time. And an optimizer will then select a new set of design characteristics to evaluate. And slowly, over the course of an hour or two, we can home in on the best design characteristics for that person. And if we apply this to something like running with ankle exoskeletons, we can reduce the energy cost by about 25% compared to wearing the device unpowered. We've applied this technique also to walking at a typical self-selected speed with ankle exoskeleton assistance, or to trying to maximize self-selected walking speed on a self-paced treadmill here. And in both cases, optimized ankle exoskeleton assistance can improve energy cost or speed by 40%, which is very large improvements. And this applies to a wide range of circumstances. For example, here we have a hip, knee, ankle exoskeleton where we can improve performance while walking at fast speeds, walking slowly while carrying heavy loads, or walking at steep inclines. And in each of these cases, we found that we can approximately halve the energy cost of walking. So we've made substantial progress in solving the primary challenge in designing exoskeletons of prosthetic limbs. We can now identify what the human needs from their device. So we're very excited to start applying this technology to help new populations and new outcomes and out in the real world. So right now we're testing similar protocols among older adults where these are people that are at risk of mobility loss, and we're finding similar improvements in energy economy and speed, which is very exciting. We've also begun tests in which we challenge people's balance and then measure their response to those challenges to understand their balance ability. And we're working on developing devices to help them to recover. And finally, we've begun transferring the design characteristics we've identified in the laboratory into autonomous product-like devices. And under these real-world conditions, we can optimize, and we've got some very exciting initial results in improvement in energy economy and speed. And this work is led by Pat Slade, who will be speaking in the next session. Now, as scientists who are working in an area that has specific development aims, I think it's very important for us to be honest when our work doesn't pan out, when things don't actually benefit the user. And so I want to mention also, and this can be a little bit of a problem for our field, I want to mention that our techniques have not been successful in improving performance with prosthetic devices. For example, this prosthesis we developed has 3 independently controlled digits that first sense and then cancel out the effects of uneven terrain. And this is one of the biggest complaints that people with amputation have. Unfortunately, none of the approaches we've tried with prosthetic limbs have improved energy economy, balance, or speed for people with amputation so far. But fortunately, we have excellent tools for iterating through new ideas. And if we're honest about what works and what doesn't, I'm confident that we're going to find ways of not only restoring locomotor performance, but enhancing it beyond typical limits. Thank you.
Excellent. Thank you, Steve. Any questions from the audience? Yes, go ahead.
Hey, thank you for that really exciting talk. I'm curious, and maybe I misunderstood, but one of the things that humans also do is learn how to use the devices better, right?
Yes.
And I'm curious how you either model that or if it's not a problem, and how you would especially compensate for it in prosthetics.
That is a really important issue. So while the device is learning to help the person is also learning how to use the device. And these are simultaneous processes. What we found, and we've actually studied this explicitly, and found that the optimization actually happens substantially faster than the learning in the person. And it can take hundreds of minutes of exposure for a person to become truly expert in these devices. So fortunately, because there's time separation, we can count on the device to respond first and sort of track the person. It's a really good question.
It looks like in your test rig, you kind of get your loads for free because everything's actuated off-site. What are the, and that's, I think, helping your efficiency numbers, which I'm sure you would agree with.
Absolutely, yes.
What do the numbers look like once you like have batteries and actuators?
Yes, so the reason that we report the improvement compared to wearing the device unpowered is it separates out this benefit of assistance from the cost of putting on the device. The cost of putting on the device has to do with minimizing mass and so on. So it's about that part is about clever mechanical design. And our system is not designed to minimize, say, the worn mass. We're currently doing experiments. I think Pat would kill me if I gave you numbers right now, but we have a few participants through, and you can get very large improvements with untethered devices as well. Yeah, there's some additional mass for motors and so on, but you also cut mass by being specialized.
Excellent, thank you.
Thank you.
Up next, we have Sergey Levine.
As we learned from Percy's talk, among others, if we want to get good generalization with modern machine learning systems, we need large, high-capacity models and large data sets that are very representative of the real world. Now, this might be a problem in robotics. You could say, well, in robotics, isn't our data very limited? In principle, this shouldn't actually be a problem, because if robots are autonomous, they should be able to collect their own data. So if we do things right, data should be plentiful. And this is, I think, a really important challenge facing robotic learning. Solutions we build with small data sets rely on human ingenuity and carefully crafted human-specified prior knowledge. This doesn't scale well to open-world tasks, though, because in those open-world domains, it's really the methods that use large data sets and powerful models that perform the best. So if we want robots to work in open-world settings, we're going to need to somehow dive into the deep end and actually be able to build scalable methods driven by large data sets. I think there are some things we need for this. One of them is to be able to train autonomously with minimal human effort. Get the human interventions out of the picture and have robots that can collect their own experience so that we can train them for a long time. At the same time, initialize everything from large shared data sets. Don't recollect data from scratch for every experiment, but actually have a shared data set in the same manner that ImageNet has worked for computer vision. What's the equivalent for robotics? Pre-train from offline data to initialize the model with some basic competence, and then fine-tune it in the real world autonomously so that it gets better and better. I'll tell you about some research we've done along each of these directions. Here's a dexterous manipulation task. This robot is trying to pick up this object and then reposition it in the hand. Now, if you want to train this autonomously in the real world, you need some kind of mechanism to reset between trials. In some of our past work, we actually used a second robot that was programmed to do this. But that's, of course, not an automated or scalable approach. What if we have a robot that's learning many tasks at the same time, such that the different tasks reset each other? Then you could have a fully autonomous training procedure, which is shown here. We turn on the robot, then the student running this experiment goes home, does some homework. In the meantime, the robot is learning. At first, it learns how to move the object around on the table. Automatically, as it progresses, it switches between different tasks, starts learning how to pick up the object, and once it has mastered this skill, then it can start to learn to reposition it in the hand. All autonomously. This takes about 60 hours. And because the method is fairly general and fully automatic, the same basic principle can be applied to learn other tasks. For instance, you could learn to pick up a pipe connector and plug it in. If it fails, it deploys another task to reset, try again, and eventually succeeds. So the basic principle is that by learning multiple tasks simultaneously, you can have robots that make the learning process fully autonomous, and then you can scalably have them run for long periods of time with minimal human effort. The amount of data you're collecting is decoupled from the amount of human effort that's put into it. And the same principle can be applied to other domains. So we've applied it, for example, to robotic locomotion, where a robot can fall down and get back up again and keep trying. Or on the right side, cleaning up a room, where a robot putters around, picks up objects, puts them back down, and practices the cleanup task. We also need to collect large data sets that we can use to bootstrap robotic learning. To that end, we collected a data set that we call a bridge data set. The point is that we would like to be able to have a data set that everybody could use for new tasks in new domains. This data set consists of 7,000 demonstrations in 10 different environments and 70 tasks. It's designed to be reusable by other researchers in new domains for new tasks. That's why we have multiple domains and multiple tasks, so that if someone else has a different lab and a different task they want to learn, they can combine it with this data and get better generalization. So here's an illustration of the scenario. We have the bridge data set, which has many different tasks in many domains. And then in some new domain, you have a new task. Now, these tasks are all themed around kind of kitchen manipulation tasks. And then maybe you have a new kitchen and a new task, in this case, to put an object into the pot. you could combine the data set together and have a multitask training process or a pre-training and fine-tuning process. Here's an illustration of this where we put the robot into the kitchen in our building, which we hadn't trained on before. And then we wanted to train the robot to quickly wipe a plate. We combine a small amount of data for the plate wiping with the bridge data, and the robot can wipe the plate successfully. If we didn't utilize the bridge data, then that small amount of demonstrations is insufficient to perform the task. So maybe this is the beginnings of a kind of data set that we could reuse and start from every time we want to learn new robotic skills. But of course, in reality, we don't want to rely on demonstrations. We want the fine-tuning process also to be autonomous. We've studied this in a project called visual affordance learning. Here, the problem statement is that we'd like to leverage prior data to explore a new environment by proposing likely goals and then adapt to the new environment automatically so that we can then carry out user-specified goals. In this example, we put the robot in an environment where there are some objects. There's, in particular, a lid with a really strange handle. The robot will hallucinate possible things to do, some of which involve moving the pot, some of which involve moving the bowls, but some of which involve actually manipulating the lid. It'll practice in that environment, trying to carry out those affordances and fine-tune its policy so that when the user then gives it a goal, in this case to put the lid on the pot, of course, it can perform it with a much higher success rate. So the way this works is that you have, again, a prior data set of many different behaviors. You use it to learn a goal condition policy, and also an affordance model that you can use to propose possible goals to practice in a new environment. So the affordance model sort of tells you, what could you do in this setting? The robot goes into a new setting, uses the affordance model to predict what it could practice, practices that autonomously, uses that to fine-tune the policy, and then when the user gives it a goal, it can hopefully perform that goal. So to summarize, I talked about these three things that I think we need to be able to scale up robotic learning. Train autonomously with minimal human effort so that you can train for a long time, and the amount of data you're collecting is independent of the amount of human effort going in. Initialize everything from large shared data sets that can be collected once and reused repeatedly, and then develop learning frameworks for pre-training from offline data, and then fine-tuning with autonomous online training using things like reinforcement learning. Thank you very much for listening.
Excellent. Thank you, Sergey. Any questions? Go ahead.
Great talk. Super interesting. I was wondering, when you train offline on first like a bunch of tasks and then fine tune after, like how do you keep the robot from forgetting like what it learned during offline training?
Yeah, that's a very good question. So this is what we call negative transfer. Well, first of all, you don't actually have to worry about that. If you really just want to learn that new task, you can simply take your pre-trained thing, fine-tune it to your task, and that's your model for this task. If you do want to avoid this, you can simply keep cycling the old data through it. In many cases, that will work. Not in all cases. In some cases, there's still challenges. Like you might learn something in this new domain that you want to transfer back to the old domains, and that's still an open problem.
Thank you.
Excellent. Well, thank you very much, Sergey. Up next, we have Jun Wu from Stanford. Setting up. Perfect. Thanks, Jun. Go ahead. Can we just make sure to get Jun's slides up?
Do we have the slides still up here? Thank you. Great. Okay. Nice to be here. So I'm going to talk about learning physical object models via differential simulation. So we want to build models for objects. And ideally, we want to do it from minimal observations. Is that possible for us to go from the single image of an object of these bases? Can we understand how it looks like? This means, can I imagine how the object will look like from a different viewpoint? Or how they will look like under different lighting conditions. This also includes, can we model how it sounds? If we click on it, if there's a collision between these objects, how the sound will be like. I try to make sure sound work, but I think sound is not playing. That is fine. You can imagine how these bases sound like. But of course, also how it feels and how it behaves. If I push the base, what's going to happen? So if we can do this, if we think about it, if we can build a data set of these kind of things and virtualize those objects, it will be incredibly useful because if you look at existing object data sets, either they're synthetic and they're not built for robotics, like ShapeNet, which has a large number of object shapes, but they have a lot of variation in geometry, but has less realistic textures, and it doesn't have, its visual appearance only, it doesn't have tactiles, it doesn't have physics. And there are real objects like YCB, which are great, And they're real, they're multimodal, you can feel it. But every object, still, if I purchase it again, I'm going to get something that's slightly different. And not to say there's also challenges in inventory management or even shipping these days. So how can we do that? Objects appear and behave in the way they are because of physics. So if you look at the image, then yeah, there are physical object models behind it, right? Behind the observations. This includes object intrinsics, like geometry, appearance, and materials, object extrinsics, like positions and velocities, and scene descriptions, like lighting and camera parameters. And I used to call it rendering, but here this is bar, so I call it simulation. The simulation actually takes these things and produce these observations. This includes images, this can also include sound and physical simulations. And in many cases, we care about the inverse problem, right? Can we invert this simulation process and to search for the object models that explain our observations? This is, of course, really hard and inner-constrained. How can we really find those latent parameters like object density distributions or reflectance functions without even knowing anything about it? So at least we thought we can make the problem a little easier if we can make a first simulation differentiable. Then you can pair them with either gradient-based optimization or learning-based methods like deep networks to invert this process. So we thought we can actually use learning physical object models via differentiable simulation to solve this real-to-sim problem. So let me give you some concrete examples. If we want to look at visual data, how the objects will look like, then you say, okay, we can do it with NERF. We have seen this before. Janette talked about it in the morning. From a few images, you can imagine how the scene look like from different places, different viewpoints. If you look at what they're actually doing, they're learning a mapping between your viewpoint and positions to the radiance field, which is RGB theta alpha, and then they put together with volume rendering, which is a technique for simulation or rendering. You can integrate the samples along the ray to compute the pixel values. The issue with NERF is it is not object-centric. It's not learning something about objects. It's learning something with only position and viewpoint as input. It learns to encode scene parameters such as lighting into representation. So you cannot imagine how the scene will look like if the lighting changes. It's all tied to the low-level details. So it's not object-centric because the parameter is learned. It's not about intrinsic object properties. So we thought, can we learn something that's specific about objects? That is how this object reflects light. If I parameterize it, not only as the position where I'm looking at, but also the input light direction and output light direction, can I learn this? We call it a scattering function that is specific to this object. So we separate what is intrinsic to the object, that is the light transport on the left, and what belongs to the scene, that is how light travels. And the second part on the right, we can do simulation, we can do integration. On the left, how object reflects light. That's hard to model, so we can do learning. And by putting this together, we can do flexible scene rendering with inserted objects. We can imagine how the scene will look like if I move the objects, if I change the lighting conditions, if I change the camera parameters. This is joint work with Michelle, who was there, and Tom Funkhauser, who was also at the back. And you can insert objects from images, a few images of these real objects, into synthetic objects, actually, but into real scenes. So this is a picture of a real scene. I have a few pictures of toys. I want to imagine how they will look like. If I directly put them together, that doesn't look right because you don't model shadows, inter-object reflections. But with learning object scattering functions, you can now do realistic rendering, imagine how the scene will look like with these virtual objects inserted into real scenes. This is about how our efforts on learning using physical simulation to learning object visual models. But what about sound? Why would object make sound? Object makes a sound, and it's not going to work because they vibrate. If I click on it, there's collision, but then they vibrate. Right? So you can actually do modal analysis and understand, okay, there are vibrations in 3D, and objects make sound at a number of specific locations based on its geometry and physics. So then you can actually do modal analysis to compute these frequency modes. And for every frequency mode, of course, there's frequency, there's damping coefficient, and there are gains, amplitude. And then, of course, there comes in the interactions or the impact forces. And these things you can say, they got convolved with the impulse responses. Right, so for every collision, okay, there is a sound that the object makes at specific frequency mode with specific damping coefficients and gains. You can do a convolution, you can synthesize a waveform, and you can compute what would that spectrum be and compare that with your now auditory observations. And you can make the whole process differentiable so that you will be able to optimize, or you can use learning, but here is an example of optimization. You can search for where the collisions are, and what the impulse responses are, including their frequency modes, damping coefficients, and gains. This is drawing what Janette was here. And finally, we thought we can move from a single object, what about to a data set of objects? To actually build, we call object folder, because we built upon an earlier idea in AI called object file, that you try to parameterize objects, modeling their multi-sensory input, visual, auditory, touch. The goal is we want to build a virtualized object data set that captures how we see, feel, and interact with objects, and so that it's much easier to do a lot of experiments that we have to redo with physical objects, and to capture all these different physical aspects of the object. Yes, this is the last slide. So we want to make it easily accessible to the community as a standard benchmark for multisensory learning, and hopefully be agnostic and compatible to different robotic virtual environments. And I don't have time to go into detail of this paper, but this is a Coral paper that also we have a poster outside afterwards. Thank you.
Thank you, Jajun. So Jitendra, there we are. Okay, so you can just come up. Any questions for Jajun? So I have a question. Have you tried closing? I'm imagining for grasping things, there's enormous potential applications. Have you tried closing the loop?
A little bit, yeah. For object folder, one of the experiments that we did in the Coral paper is to test how that may help, or to what extent the sim-to-real grasping can actually help there. So, and also we're trying to make it more realistic and doing experiments with real robots. Back then in the Coral paper, it was mostly in simulation, partly because of COVID, and we don't have a building, but hopefully, but right now we're doing some real robot experiments to actually calibrate the sim-to-real transfer performance.
And do you have a feeling for how much this, let me let the audience ask.
Yeah.
Go ahead.
Yeah, I was wondering if you have any ideas how to extend it to the sensory, the touch sensing, for example.
Yeah, we are working on that. The object folder does have touch, and then we're also working with Janette and also Wenjun Yuan from CMU on integrating their latest tactile simulation into.
Yeah, I was wondering what kind of tactile sensors were you thinking of integrating, like something like gel side?
Right now it's gel side. Yeah, but actually in the object folder folder it's not gel side. It's actually Texan, but we are switching to gel side.
Okay, thank you.
All right, excellent. Thank you, Jajun. Up next we have Jitendra Malik from UC Berkeley.
Thank you. Okay, so I'm going to talk about learning to walk. Okay, so this is this work. Most of this work was published as a paper at RSS, and we also have a poster which Ashish is here, and he'll present that, so you can get more details there. So what's the problem we're trying to solve? It's legged locomotion with a quadruped, and even though I'm a vision guy, this robot is blind, so it's going to be just with proprioception and so forth. And the goal is to train the robot in simulation, then put it out in the real world, and it should work out of the box. Okay, no sim to real stuff. Okay, and one policy for all conditions. Okay, and I'll just show you some examples. Okay, so I don't know if you can hear the sound. No. Can you hear the sound? Or okay, so right. So this is a blind robot. So its foot reacts against the rock, and then it tries to keep moving. This is going downstairs. It's exactly the same policy. Okay. Okay, here it's in vegetation, and it doesn't know that there is a dip, but it has to respond to that and not break its legs. Okay, different kinds of terrain like wet ground or sand on a beach and so forth. Same policy always. Okay, this is loose mud on a construction site, so it's unstable footholds. Okay, this is even more tricky, which is like these planks. It doesn't fall. If you use the standard controller, it will fall. Okay, it's important that I do this not just at safe, slow speeds, because a robot should be able to move at different speeds. Same policy. Okay, this is velocity condition. So it's been commanded to go at certain speeds at certain times. Okay, so that has been programmed in. So it's been told to go at a certain speed, then automatically the gate changes. We did not program in any gates. The gates are emergent. Okay, and then it goes at so we have just told it go at 0.5 meters per second, 1 meters per second at different times. All these gate transitions emerge automatically. And just to show you some more examples of stuff with trickier movements. So it can go really fast, and these are cases where the human is pulling at the robot and there's a flight phase and all that. Okay. Okay. So more examples. So you can see there's a flight phase, right? Okay. So it's one policy, all conditions, no gates or footfall patterns are programmed. Okay. Everything is emergent. You train in simulation and then you put it out in the real world. Okay. So how do we do this? The central idea is that we need to have a policy to walk, but it always needs to adapt. So a central aspect of human perception and human motor control is that we are always adapting. When I walk in sand, I have to use a different sort of thing than when I'm walking on hard asphalt. And we adapt very quickly. We can adapt in like 0.1 of a second. You don't have the time to spend 5 minutes trying to adapt. It has to happen in like 0.1 second or half a second, otherwise you will fall and break your legs and that will be the end of you. So the central issue, so how do you do this? So the key idea is that there is a base policy which is trained in simulation, but simultaneously you train an adaptation policy, and the essence of this adaptation policy is you need a signal to tell you that you are in different conditions. You are walking in sand versus walking on hard road, whether you've got a weight on your backpack or one of your legs is in trouble because it's sprained. So this adaptation policy, what makes that work is that it is estimating what the extrinsic conditions are based on the proprioception. So every time I am commanding some actions, right? So when I am walking on sand, I try to make the same actions as when I am walking on hard ground. But because the ground is different, it takes me more effort to pull my foot out of the sand. So knowing the sequence of last few states and my actions enables me to estimate the extrinsic conditions of the environment, and that's what the adaptation module does, and it does it at 10 hertz, so 0.1 seconds, and that's it. And there are all the technical details. So we train in simulation with a fractal terrain. We also can train this observation, this adaptation module in simulation and that's the part you have to read the paper for or go to the poster for. Basically the discrepancy between expected movements and actual movements. And it's a general technique. It applies across the board. And here's an example. I'll conclude there. Okay. So there's Ashish pouring some oil. So basically now it's a slippery situation, right? Literally a slippery situation. And the robot is going to try to walk. Its legs are going to try to slip. Okay, so it slips, but then it recovers. And why it's able to do this is and what's happening is that the adaptation module is estimating the states of the extrinsics and it is changing, and that's what you see in those curves. So basically that adaptation occurs in 0.1 seconds. Thank you very much.
Thank you very much, Chandra. Go ahead and ask a question.
Thank you for the talk. I had a question. You alluded to like how humans like perceive the world around us. I was very curious, is there a reason why your robots are blind?
It's because we know that blind people can walk. So we started with blind robots, and currently our robots have vision, and that's of course needed for long range reasoning and avoiding obstacles and so on. So the longer version of this talk, I would show you the walking robots with vision.
Thank you.
Yeah.
Go ahead. Jitendra, we have one more question if you don't mind.
Do you have an integer state in your?
Do I have any what?
Integer state. Or all other states are continuous, or do you have integers as well?
They all well, a foot is the foot touching the ground is 0, 1.
But how about the phase?
See, the state is joint angles, so those are all continuous variables. But is the foot touching the ground is binary.
Okay, maybe take it offline. Okay.
Yeah. Thank you.
Excellent. Thank you very much. Great. Up next, Marco Pavone. Go ahead, Marco from Stanford.
Hello, everyone. It is wonderful to attend BARS in person again. I would like to.
Very sorry about this. Before you get going, can I just ask all of the spotlight presenters to please start lining up on the right-hand side of the room, and then you can continue.
Yeah, before you interrupted me, I wanted to thank you and Dorsa for organizing BARS and, of course, their students. Anyway, during the past year, together with several partners, we have kicked off a fairly large project sponsored by NASA on the topic of safe AI for future aviation systems, which I'm very excited to lead. In a nutshell, the goal of this project, which is a collaboration among several institutions across the United States, is to develop algorithmic techniques to enable the trusted deployment of future aviation systems that use machine learning models, or more broadly, AI techniques as part of their decision-making process. Our technical approach entails 3 main thrusts. First, devising tools to verify, robustly train, and add structure to learning-based components with a focus on deep neural networks. Second, devising tools to monitor at runtime those components of the autonomy stack that are learning-based, as well as techniques to handle possible failures through adaptation and robust control. And third, devising airspace management algorithms for the setting where some of the airplanes could be partially automated or even completely autonomous. Collectively, the goal is to establish a pipeline that allows us to build systems with strong offline assurances, which can then be complemented online with the principal fault detection, isolation, and recovery techniques. Our work is integrating and validating by leveraging a variety of testbeds, from photorealistic testbeds all the way to real-world flight testing. Now, in this context, a key research topic we are pursuing in my lab at Stanford is that of runtime monitoring. The premise is that no matter how well a machine learning model is trained and optimized, it can still perform poorly, as it might encounter situations that are very different from those encountered during training. In other words, a key limitation of machine learning models, such as deep learning models, is that they are largely only as good as the data they are trained on, which is one of the reasons why they might fail at runtime. Concretely, consider the setting where an autonomous aircraft is tasked with tracking the center line of a runway. And consider a perception, a deep neural network, which translates high-dimensional visual observations, such as the image of the runway on the left, to an estimate of the state of the system, for example, lateral displacement. This estimate is then used by a downstream controller to produce an action to take. The deep neural network is trained on labeled example of observation state pairs assumed to be drawn from some joint distribution. This joint distribution, crucially, is a function of the environment. And, of course, is a function of unobserved context variables, such as weather, time of day, lighting conditions, and so on and so forth. When the context or environment change, for example, we are operating at night, the observation may be quite different from those seen in training. And such auto-distribution observation can lead to faults in perception, for example, an erroneous estimate of lateral displacement, and thus negatively impact the closed-loop performance of the overall system. So to enable safe, trusted deployment of these learned models, it's critical we can detect and isolate these faults at runtime. For this purpose, we have been working on equipping deep neural networks with a monitor which can provide a signal to detect anomalous inputs during operation. Specifically, we have recently developed a novel framework, SCUD, which stands for Sketching Curvature for Auto-Distribution Detection, which is a general-purpose model-agnostic approach to adding an uncertainty measure to pre-trained deep neural network models. In a nutshell, SCUD leverages the local curvature of deep neural networks to reason about epistemic uncertainty. And more details are in a paper we have recently published, authored by Apur Sharma, a PhD student in my lab, and Navid Azizan, a former postdoc in my lab and now a faculty at MIT. We have tested this approach on a deep neural network system used for autonomous aircraft taxiing. The input to this network is the image from a wing-mounted camera. And the output is the distance of the aircraft from the center line of the runway. We introduce anomalies into the dataset by changing time of day or weather conditions, which are different from those seen at train time. In this simulation, we first test the runtime monitor on images similar to those seen during training, that is, in good lighting conditions. On the right-hand side, I plot the output of the runtime monitor as a function of time. As we switch to sunset condition, which is a condition that was not included in the training data, we see shadows. These shadows cause large errors in the estimate of lateral displacement. But fortunately, this situation is picked up by the monitor, whose output is significantly higher than in the nominal case. That is, at least we know that we are operating in a dangerous situation. The key takeaway is that the runtime monitors are key to build high-confidence machine learning systems by keeping the machine learning models constantly in check. So we're currently working on developing decision-making logic that use the signal from such runtime monitors to seamlessly transition from an AI-based policy to a recovery policy in case of an auto-distribution event. We have developed a simulator along with the dataset to benchmark auto-distribution techniques as well as verification and falsification techniques. If you're interested, you can have a look at our GitHub page. And I'll conclude with a short video of some research experiments I'm very excited about. We carried out on an International Space Station, where we tested a robotic system to grasp objects in space. In this particular case, a free-flying robot is attaching itself to one of the walls within the International Space Station. This is a collaboration with the group of Mark Kutkowski here at Stanford and NASA Ames. So if you're interested in learning more about machine learning for safety-critical systems and their application to other aviation or spacecraft systems, feel free to reach out. Thank you.
Thank you, Marco. That's really interesting. Do we have a question?
Hi, Marco. Thanks for the talk. I was curious. This seems kind of like a chicken or egg kind of a problem in the sense that you have, an initial distribution that you're working with from the trained DNN. Do you see any applications for this signal that you're using to identify outliers in the initial training process of the DNN as opposed to its implementation in the online?
Yeah, that's a great question. So basically, runtime monitors can use both offline and online. It can be used offline in a sort of a data lifecycle loop. Basically, you identify gaps into your models, and then you can retrain them. But also online, to basically inform downstream policies whether you are operating auto-distribution. So I wouldn't call it a chicken egg problem. I would say dual purpose type of tool. And each one has its both benefits and weaknesses. But the premise here is that for safety critical systems, no matter how good your model is trained, most likely sooner or later are going to be in a situation where you're operating in a setting where generalization really doesn't apply. So how do you detect those and you recover gracefully from those? This is one of the big open problems in the domain of robot autonomy for safety critical systems.
Thank you.
Okay, we have time for one more quick question.
Hi, Marco. Thanks. That was a great talk. I was wondering if you benchmarked your out-of-distribution detector against something simpler like ensemble variance or something like that.
Oh, yes, we did. Yeah, of course.
That's like strictly.
There are a number of pros and cons. For example, one of the advantages here is that we don't have to train an ensemble of models, but actually we can just apply to a single individual model. But in the paper I mentioned, of course, we have benchmarking with ensembles along with other methods for auto-distribution detection. Of course,
thank you.
This is becoming a fairly popular topic.
Excellent. Well, before I hand over to Sid, let's just thank all of the speakers in this session again.
Hey folks, we're coming up on our second set of Spotlight Talks. We have some amazing talks from our sponsors, about 2 minutes each, followed by another, quick 1 minute per each of the amazing students lined up on your right. We're going to ignore Mark's advice this time and clap between speakers. And with that, Olga, take it away.
Thank you very much for coming. My name is Olga, and I will talk about medical robotics and give a sneak peek of what we do in Auris Health. So we are focusing on endoscopic robotics, and specifically we go after 3 areas: lungs, kidneys, and GI tract. So here is a pretty slide with scary numbers. Lung cancer is the #1 killer cancer globally, and every 3 minutes there is someone dying in US because of lung cancer. In Auris Health, we dream and aim to change that. So what we do, we have a unique scope that, this is not how it should progress. So we have a very unique scope that can go very, very far, and it has vision on top of that. We've developed hardware in-house. We have robust software and state-of-the-art navigation and AI that helps physicians to reach those far places. So our navigation, it is using latest research in computer vision, the data from electromagnetic field, and the robotic insertion. So now it's much better. Hello. Should I restart? No, I'm good. Okay, so if you have any questions about the visuals that you had before, talk to me, okay? So now the most exciting, take a picture of this. This is about the positions that we have in our team. So I lead algorithms and AI team, and what we do, we push the innovation with the context-aware intelligent algorithms. We have internships and full-time positions in the area of computer vision research, applied machine learning, and medical imaging, and augmented reality. We have today in this room software team, AI team, and controls team. They are all over the place. You can talk to us. And for the controls and robotics team, this is an amazing team that is diving deep into the algorithms at the heart of the system. Their opportunities are in rigid inflexible robotics, complex algorithms, and data analysis. Any questions? Please find me in the back. Thank you so much. Again, thank you.
Okay. Hi, I'm Mark Palatucci. I'm excited to tell you about Waymo. So Waymo is an autonomous driving technology company. We started as Google self-driving car in 2009, and in 2016 we became our own independent company. Our mission is to make it safe and easy for people and things to move around, and we believe that AV technology holds the promise to improve road safety and also offer new mobility options to millions of people. We deploy our driver in 2 categories. Waymo One is our driving service, and Waymo Via is our commercial goods delivery service, which includes both trucking and local delivery. Over the last 10 years, we've driven autonomously over more than 20 million miles on public roads, 20 billion miles in simulation in 25 cities across the United States. And we recently hit a really big milestone for autonomous vehicles. Last year with Waymo One, which we launched in Phoenix, 100% of our rides are fully autonomous with no human driver behind the wheel. We're now looking to expand to more dense urban environments, and we recently announced our Waymo One Trusted Tester program, which allows San Franciscans in the program to hail an autonomous ride in one of our new all-electric Jaguar vehicles, which I'll give you a sneak peek of. Is there audio? No audio. Last slide. If you're interested in doing research in autonomous vehicles and robotics, please consider Waymo Open Dataset. It is one of the largest data sets of perception and motion data from autonomous vehicles. Thank you, and we'll be in the back if anyone wants to chat.
All right, does this one work? Yeah, okay. Hi, everybody. It's great to see the top third of so many faces here today in person. My name's Troy Adebar. I'm from Intuitive. We're a medical robotics company just down the road in Sunnyvale, and I'm going to give you a quick 2-minute introduction. So at Intuitive, we build and sell medical robots, and we've built and sold quite a few medical robots. So there are thousands of Intuitive systems installed in hospitals all around the world. They're in every state, and if you can see here, on average, we start a procedure with an Intuitive system about every 25 seconds, and I've got about 3 Intuitive procedures before I get signs held off and get kicked off. That was a joke. There's 2 main systems I'll tell you about. So if you've walked by our booth, if you've heard of Intuitive, there's the Da Vinci. It's a teleoperated surgical system. It's used for minimally invasive surgery. So the physician sits in an immersive environment, control tools inside the patient. There's also Ion. So this is the system I work on. It's a flexible manipulator. It's used for driving a catheter through the airways of the lung, out to the edges of the lung to take a biopsy for diagnosing lung cancer. So I really like working at Intuitive because it's 2 things. It's a medical device company, and then it's also a technology company. So as a technology company, at the company, we get to work on like really interesting problems in computer graphics and software engineering, and image understanding and registration and control theory. But because it's also a medical device company, the technology you work on makes a direct, measurable impact in patients' lives and in the lives of the physicians who treat them. So if you're interested in the technical problems or if you're interested in the applications, please come talk to some of us from the Intuitive crew. There's 5 of us here and thousands of us worldwide, and we do all enjoy a friendly chat. So please come speak with us. Thank you.
Hello, so I'm Dave Johnson, the co-founder and CEO of Dexi, and we are an automation company for the food industry, or more generally, we make robots which make food. Our mission at Dexi is to make the lives of kitchen staff better. We're making it easier for a chef, whether they're at Chipotle or in a commissary kitchen, to prepare meals for hundreds of people. With that, the easiest thing is to watch the robot in action. And do we have sound for this? To get this to work and build a general solution for not just one recipe, but many recipes without changing the way the food tastes, we've had to solve a lot of challenging problems. For fast service, we have to always run the robot at its dynamic limits, including in contact with material. We need to store the utensils in the containers to satisfy food safety regulations, so we have to solve a moving peg and hole problem. We need precise portions, so our learned policies have to understand material physics and how the materials interact. We need to be able to manipulate a diverse set of ingredients, so those policies have to generalize and work with different viscosities and friction coefficients. We can't just use an ice cream scooper to handle all ingredients. We have to work with different utensils like tongs, spatulas, and spoons. And we have to be able to handle a variety of situations. So we can't leave food in the container. We need different strategies, which will work with many different tasks. And so we're interested in all of you because we want to solve the next challenge and go into different tasks inside the kitchen. And we're hiring across all domains for machine learning, robots, and everything. So check us out at dexi.com/careers. Thank you.
Hi, I'm Fred, co-founder of Multiple Labs, and we apply robotics to the manufacturing of next-generation drugs. So basically, medicine is becoming very personalized, and so the medicines of the future will be tailored and are already being tailored to the single patient. The problem is that right now, they are made by hand, and you can't just hire 1,000 scientists and cram them in a clean room and ask them to make 1 million drugs. That would also be a nightmare from the regulatory point of view. So we're not making robots that replace people, we're making robots that do a job that people cannot do. And we really believe that the only way to bring these drugs to patients is by, scaling, basically building robotic factories for medicines. And so here you can see one of our robots. We deploy this in some of the largest pharmaceutical companies worldwide. They are modular, they are cloud controlled, and most importantly, they are designed to make drugs cheaper. So our customers are the pharma companies, but the purpose of the robots is to bring down the costs. So we are patient aligned, and that's very important to us. Our vision for the pharma factory of the future is basically a swarm of robots, cloud controlled, to make drugs for every single patient and very efficiently. We're hiring mechanical engineers, software engineers, everything in between. So these are cloud controlled, robots. So pretty much if you're in robotics, we're interested in talking, and feel free to pass by and talk to me. Thank you very much.
Hello, everyone. My name is Liang from BYD Research, Robotics and Autonomous Driving Lab, IAL. Our lab works on mining and construction robotics. Excavators are widely used in mining and construction. However, the industry faces a lot of challenges like the shortage of skillful operators, safety issues, and prolonged work hours. We tackle this challenge by proposing and developing autonomous excavator system, AES. So as the video shows, our system has composed the perception, planning, control, and the software modules. And our hardware consists of various sensors, LiDAR cameras to perceive the surrounding environment. We develop a perception system to perceive the complex outdoor environment, like terrain, logs, and various situations. And we validate our system on the real-world situation, the waste recycling disposal site. And our system can achieve 24 hours continuous operation without any human intervention. Furthermore, the system has been used daily by the user for their daily operation. And we also test various other scenarios and collaborate with the major heavy equipment machinery companies. The full video can be accessed online. Our team also working on other robotic projects like the perception for vehicle uncommon states and human character and estimation, as well as other projects. Finally, our team is co-located at the Silicon Valley and the Beijing office. And we have opening for full-time researchers in robotics and 3D vision. And we also are interested in hiring the interns all year round. So welcome to contact us. Thank you.
Hello. My name is Avi. I'm a research scientist at Google working at the intersection of machine learning and robotics. At Brain Robotics, our goal is to make robots useful in the real world, and we intend to do so through machine learning. As a result, we focus a lot on techniques like deep reinforcement learning and imitation learning. Here's one recent representative project, MT-opt. This is a system for doing multitask deep reinforcement learning in the real world for robotics tasks, and we've successfully trained the system to do a wide variety of object manipulation tasks directly from visual inputs. Another project in a similar vein of large-scale robot learning is BC0. This project focuses on imitation learning, and we collected 26,000 demos across 100 different tasks, each of them paired with a natural language instruction, which allowed us to learn a policy that, given a new task, can be prompted to perform that new task through natural language. Another line of research focuses on high-speed robotics, so tasks that might require really high-speed control and precision, like playing ping pong. Once again, using a combination of imitation learning and reinforcement learning methods to train these policies. We also have a lot of work happening in robot locomotion. For example, in this work, the goal was to combine optimal control with reinforcement learning to learn policies that can walk on uneven terrains using visual input. So if any of this is interesting to you, there are many ways to participate in the research that's happening at Google targeted towards students. One of them is through conventional research internships that are 12 to 14 weeks in length and require full-time engagement. And then the other way is through flexible student researcher positions. To find out more about them, go to careers.google.com and feel free to ask me any questions as well. Thank you.
We'll be switching to student presentations, followed by one more sponsor presentation at the end.
All right. Hi, I'm Patrick, and I'm going to be talking about monitoring the calories you burn during exercise. Everybody knows that obesity is an epidemic, and you can't manage your weight without understanding how many calories you're burning while you're exercising. So what we've done is we've built a data-driven model to use wearable sensor data to track how many calories you're burning. So existing tools like smartwatches have an error of 40 to 80%. So don't pick how many cookies you're going to eat based on the step count. But what we did was we used a bunch of different wearable sensors. We selected the most informative sensors. We trained a data-driven model combining biomechanics and machine learning to estimate the calorie you're burning. And then we validated this with a new group of adult group of participants to represent an adult population. And so what we found is our method is very accurate, about 10% error, and we think it can improve health. So if you want to talk about health and machine learning, come talk to me. Thanks.
Hi, my name is Burjan, and I'm from the UC Berkeley Auto Lab. I'm here to talk today about recovery RL. So learning to perform tasks in unknown environments is very challenging because it involves taking risks and exploring aggressively. And this can lead to constraint violations, which can be very costly and have like real-world costs and consequences. To take a step towards addressing this, we propose Recovery RL, a general purpose framework that executes across two policies: a recovery policy, whose only job is to recover back to safety, and a task policy, whose only job is to perform the task. We additionally learn a risk metric that adaptively switches between these two policies during online execution. The method uses a small set of offline examples of constraint violations in order to avoid experiencing constraint violations online, which may be more expensive. To further reduce the need for these demonstration samples, we also propose MESA, a method that extends Recovery RL to rapidly adapt its measure of safety to a new environment with similar dynamics. We present a suite of simulation and real robotics experiments suggesting that Recovery RL is more efficient and safer than baseline approaches. If any of that sounds interesting to you, please come by and check out our poster. Thank you very much.
Hello, my name is Frederick Ebert, and I'm going to present our work, Bridge Data, Boosting Generalization of Robotic Skills with Cross-Domain Data Sets. So the big challenge in robotics is that in real-world robotic learning, people always recollect data from scratch for every single task, and that's very wasteful. So the main question we're trying to answer is, what would it take to reuse data across many tasks and many environments in robotics? And our hypothesis is that this would require a data set with many different domains and many different tasks. And that's exactly what we did. So we collected 7,200 demonstrations in 10 different kitchen environments across 70 different tasks. And the data is open source and available. It's on a low-cost robot for easy reproducibility. And this allows us to transfer a task from the bridge data, which we call, to a target domain. And if we jointly train with this bridge data and if only a few tasks in the target domain, we can zero-shot deploy a task in a new environment. If you want to learn more, come to my poster. Thank you.
Hello, my name is Michael Lingebach, and I'm a PhD student here at Stanford. One common theme today is the interest in developing robots that display human-level intelligence. To that end, I would like to introduce Behavior, our new benchmark in simulation for long-horizon activities. Our behavior includes 100 household activities drawn from the American Time Use Survey. Activities such as packing lunches, cleaning bathrooms, defrosting the freezer, and packing school supplies. Each initial and final condition is annotated by humans, and we provide 500 human virtual reality demonstrations. These activities go beyond simple kinematic state changes and include states such as cooked, frozen, stained, soaked, and more. Behavior is powered by an expressive domain definition language, BDDL, which allows for defining initial and final conditions using predicate logic. We also provide utilities for sampling infinite combinations of starting scenarios, and a benchmark suite of metrics for evaluating your agents. Existing baselines cannot solve mostly behavior activities, so we believe this is an exciting area for future research. Please come see me at my poster if you're interested in learning more. Thank you.
Hello, everyone. I'm Rohan Gao. I'm currently a postdoc at Stanford. So I'll briefly fill in more details of the work Jiajun has talked about. So it's also joint work with Yan-Yu Chang and Shivani Moore and Fei-Fei Ni. So this is a dataset effort called object folder, a dataset of objects with implicit visual, auditory, and tactile representations. So in this dataset, we have 100 objects in the form of implicit representations called object files. So querying the object file with extrinsic parameters, we can obtain the visual, auditory, and tactile data, sensory data for each object. So this is a uniform object-centric and implicit representation for each object. And we hope this can be a easily accessible benchmark to the community for multisensory learning with vision, audio, and touch. And we have attempted this task to show you on the right in this paper. And this object is also platform agnostic and compatible to different robotic virtual environments. So that's it. Thanks for listening.
Hello everyone, I am Ashish, and today I'll talk about rapid motor adaptation for legged robots. And in the 50 seconds that I have, I'll just re-emphasize the results that we have on legged robots. So in the top left, you can see all these deployment of our algorithm RMA in the wild. And I would like to emphasize that this was trained entirely in simulation and it was deployed on the real robot without any modifications or fine-tuning to the method itself. Now, if we take the same system and instead ask it to track different speeds, we also observe that it shows an emergent gait behavior. And the reason we are able to get different gaits automatically from different speeds is because we did not pre-program any gaits or used any fixed footfall sequence. Instead, we take our inspiration from biomechanics on how babies and animals learn to walk, and we just train our walking system under the constraint of minimizing energy consumption. And all the results that you see are that coupled with the task reward of walking forward or tracking a speed. Thank you and see you at the poster.
Hello everyone. Today I would like to tell you about some work we've done on learning object manipulation from videos. So we're essentially interested in learning wide range of object manipulation skills, just like humans can do. And currently the most natural paradigm for this is reinforcement learning. However, this does leave some room for improvement in terms of the sample complexity and the rewards and so on. So one way to overcome these issues is to apply classic ideas about leveraging observational data of humans in order to learn to perform different tasks faster. So as I said, it's a classic idea, but what has changed really is that we now have access to lots of data of humans doing various tasks. However, there still remain challenges, namely in developing the right representations to leverage this data, as well as not having access to the actions that the humans have commanded during those behaviors. So in our work we've made progress along both of these axes, and I would love to tell you more about it at our poster session later today. Thank you.
Hi everyone, my name is Spencer. Real-time adaptation is imperative to the control of robots operating in complex dynamic environments. Adaptive control theory promises good trajectory tracking performance for even nonlinear systems, provided that any uncertain dynamics terms enter into the dynamics in a linearly parameterizable manner with no nonlinear features. However, these nonlinear features are often difficult to specify a priori, especially for things like aerodynamic forces and interaction forces between robots. We turn to offline data-driven learning of these features that is cognizant of the downstream control task. Our key insight is that we can better prepare the controller for deployment with control-oriented meta-learning of these features in differentiable closed-loop simulation, rather than regression-oriented meta-learning of these features just to fit input-output data. We demonstrate that our model and adaptive controller outperform other methods when deployed in closed-loop trajectory tracking control tasks, especially in the face of distribution shift between training and test scenarios. Thank you.
Hi. In this work, we propose a framework so that robots can safely perform tasks despite highly uncertain dynamics. For example, a spacecraft may have captured a new payload and may be uncertain about its couple dynamics with this object. So in this case, our framework first explores to do system identification before exploiting the acquired information to perform the task. Our framework consists of two phases. Offline, first, we perform meta-learning to learn expressive neural network basis functions. Second, online, we use model-based control to compute safe trajectories to reliably solve the task. We prove that our framework guarantees constraint satisfactions at all times with high probability, and validate our algorithm on hardware, where we show that exploring online is necessary to reliably solve the task. Thank you.
Hi everyone, I'm Karan Jain from Hyperlab UC Berkeley. Modular aerial robots have been rising in popularity lately, and one such application was presented by us about a couple of years ago in the form of flying batteries, where we dock two multirotors midair to transfer power and basically extend the flight time of one of these. This work is a part of the solution to extend this work and deploy it in an outdoors environment. Specifically, we address the relative localization problem, where we have a passive quadcopter, which is flying on the top, which has a marker at its bottom, and an active quadcopter, which has a camera and an IMU, which can look at the marker, and just using onboard sensors, it can localize itself with respect to the passive quadcopter. With that, we are able to estimate the relative position, velocity, etc., and dock the two multirotors just using onboard sensors, which requires a precision of about 1 centimeters. Yeah, to find out more about this research, please find me at the poster session. Thank you.
Hello, my name is Clark Za. I'm from Hyperlab of UC Berkeley. Previously at BARS, we presented a vehicle that can collide with a wall and survive collision speed up to 6.5 meters per second. It seems like it's very exciting, and the video just froze out. And we're also very excited that we actually have a drone that we can throw at wall at will. But we are not content at that. This year we have very interesting updates in terms of like we add a new reorientation controller that allows the vehicle to rotate itself on the ground. So if its propellers is facing down, it can turn itself back and face it upwards. We also have an inertial navigation ability of the vehicle so that it can turn long flights into short hops to decrease the accumulation of error. So that you can see that we are bringing out into unknown environments. It doesn't have cameras on it. It's not using mocap. It's just navigating by itself in the forest environment. If you are interested, please show up at our poster. Thank you.
Hi everyone, I'm Adyasha, and I'll be talking about a collaborative project with the NAV Lab and TRI. It's called Precise Relative Positioning and Tandem Drifting. So far, autonomous single-car drifting has been demonstrated here at Stanford, where we localize using GPS carrier phase measurements. A key requirement for this is to resolve the integer ambiguity successfully, which requires base station corrections. To extend this to a tandem drifting case, we have to account for faster, rapidly changing dynamics between the cars and also ensure centimeter level positioning in real time. So how do we achieve this? Our approach integrates a priori constraints specifically learned from drift dynamics that helps us to adaptively constrain the search space of integer ambiguities and help us achieve centimeter level accuracy in the relative position that helps us probably achieve tandem drifting in a span of 3 years. If you're more interested in talking more about this poster, please check out my poster. Yeah, thank you.
Right. Hi, everyone. I'm Shubh, and my poster is on incorporating observation noise in the adaptive stress testing of autonomous vehicles. The existing framework for adaptive stress testing, or AST, finds the most likely failure in an autonomous driving simulation. However, AST requires the user to specify a probability distribution of the disturbances that happen in states due to observation noise, which can change based on the environment state. Furthermore, the observation noise can be high dimensional and therefore difficult to search over. Therefore, we develop an approach that extends the AST framework to find the most likely failure while simultaneously constructing a probability model of disturbances based on the search requirements. To learn more about this work, please visit me during the poster session. Thank you.
Hello, everyone. My name is Andrew Barkin. I'm a PhD student under Alice Agogino at UC Berkeley, and we're investigating physical human-robot interaction with tensegrity structures. So tensegrities are really great because they're physically resilient. You can throw them on the ground and they won't be harmed. So the idea is to ask the question, how can the robustness of a robot contribute to our ability to physically interact and communicate with a given robotic system? So instead of a traditional non-contact version of HRI, we can look at a sequence of physical interactions that can be extremely expressive and intuitive and exploit the inherent physicality of certain applications to communicate intent to a robotic system. So we developed a spherical tensegrity system that has force sensing instrumented in it that gives us the ability to detect different external forces on the actual structure of the system. And we use classification models to basically infer what type of interaction occurred. And our classification model is showing results as high as 98% accuracy in terms of recovering the type of interaction that occurred. So if you'd like to talk more, just let me know. Thanks.
Hello, everybody. My name is Masha Ikina, and I'm presenting our work on multi-agent variational occlusion inference using people as sensors. Our algorithm builds on human intuition. So if you consider the diagram on the left here, you see a green ego vehicle that is trying to turn right. It observes two cyan vehicles. There's also a blue occluded vehicle. So if the ego vehicle sees that driver 2 is slowing down or stopping, it should be able to infer that there might be an occluded obstacle ahead of that driver. The way our algorithm encodes this logic is by learning a multimodal mapping from observed trajectories to the environment ahead of that driver, which we model as an occupancy grid map. We then scale this algorithm to multiple observed drivers using sensor fusion techniques. You can see our algorithm work in the video on the right, where it successfully infers occupied space ahead of driver 33, encompassing an occluded vehicle. Thank you.
Hi, my name is Chelsea Sadrain. My research focuses on the fact that neural networks can exhibit unexpected behaviors, and if we want to use them in safety critical systems, we need guarantees of reliability. So I've been working on verifying neural network control policies and neural network estimators. For control policies, I'm mainly interested in verifying closed loop properties, like do these two cars maintain a safe distance from one another? In contrast to open loop properties like does the neural network ever jerk the steering wheel to the left? For neural network estimators, I'm also interested in properties that require modeling the system dynamics. Like, can we show that the estimated value of quantity M is close to the true value with some confidence level? And if any of these topics interest you, please come talk to me at my poster. Thank you.
Hi, hello everyone. My name is Tony Chen, and I'm in BDML here at Stanford with Professor Mark Kokoski. Today, I'm presenting ReachBot, a new robot concept in mobile manipulation that's really well suited for space and planetary exploration in cave-like environments. So ReachBot consists of a small body that has extendable, lightweight arms that can reach to near or far away rock surfaces and grasp it, up to many times its body size. So as a result, it can traverse difficult terrains similar to a large robot, but at a fraction of the cost, weight, and complexity compared to a traditional rigid link robot. And compared to similar robot of a smaller robot of similar class weight, it can move much faster and has many more grasp points per step due to its large configuration space of limbs. So here, what I'm presenting today is a planar 2D prototype of ReachBot that rolls on bearings and actually uses a motorized tape measure as its arm to explore the basic concept and to gain insights into a ReachBot-like system. Thank you.
Hello, my name is Sam, and I'm also from Mark Kokoski's lab here at Stanford. We're working on a teleoperation device that provides physicians remote access inside the bore of MRI scanners. And using the system, they can perform procedures like biopsies with the patient remaining inside the bore. So this lets them leverage real-time guidance and also streamlines the procedure. In this video, you see the teleoperator in action. Some key takeaways is that the system's fully passive, so the forces and motions are all generated by the operator and they're transmitted through the hydraulic lines. We've done a lot of demos and different experiments, so if you'd like to see more about the system and see some data, please stop by my poster.
All right, that is it for student presentations. We have one more sponsor presentation from Sanjivan at Aurora. Just look away and pretend I'm not doing any of this. Here we go. Cool. All right. Sanjivan, take it away.
Thanks, Ed. Last but hopefully not least. Hi, everyone. I'm Sanjivan Chaudhary, a technical lead at Aurora, where we work on self-driving at scale. I want to start by showing you what an unprotected left looks like to the AV. It might not seem very complicated to you, but the AV has to perceive everything that's happening, forecast what could happen as a result of different decisions, and decide how to act while taking into account how other actors may react, all at the same time. Driving is full of complex interactions like these. At Aurora, we take a learned, interleaved approach to forecasting and planning that allows the Aurora driver to reason explicitly about its decisions of how other actors will respond. Now we can picture the way this works by imagining each actor as a node in a graph. The edges of the graph tell us relationships like, is actor A yielding to actor B? Our geometric transformer net inference engine, leveraging state-of-the-art graph neural networks, enables the Aurora driver to jointly reason over the graph of interaction between actor nodes trained from expert human driving data. Let's look at a different scenario, a merge interaction on a highway. Our geometric transformer net generates a matrix of attentions for every actor on every lane. But sometimes people do unexpected things, like this actor cutting across a solid white line to merge in. Watch how the lane attentions for this actor switch from the merge lane to the AV lane as the actor cuts in. Our model quickly detects the actor is cutting in, and we slow down. Even in complex scenarios, the Aurora driver is constantly computing a huge matrix of actor attentions. We saw that both urban and highway driving are full of complex interactions. Our approach to forecasting and decision-making allows the Aurora driver to exhibit human-like, predictable, interpretable behavior on the road, resulting in a safer environment for everyone. Thank you.
All right. All right. Thank you to all the sponsors and the students for their wonderful talks, closing out the second and last spotlight session. I know 1 to 2 minutes isn't a lot of time, so now we're opening this up to the second coffee break and poster session outside. Please ask all your questions. Be back here at 4:15. Thank you.
I'm very happy to see everyone here. It's really great that everyone came out. I think we are all very grateful for the participation. So in my research group, we work on aerial robots, sort of how we can push them, how we can get them to be faster, more efficient, more intelligent, etc. And I just want to show you mostly some cool videos because we only have 6 minutes. This is some work we showed, I think, 2 years ago at BARS. We were sort of working on aerial robots that can sort of emulate some of the things we see birds doing. So here's just sort of these very agile birds flying through narrow gaps, etc. And we developed a robot, a drone that can fold itself to fit through narrow gaps. So this is doing a very fast maneuver, and then folding its arms to fit through this gap. And I want to just show some updates about this. First, slow motion, of course, why not? Can never go wrong with some slow motion videos. So we've been working on this, developing it further. So I want to show you some of this work where we're really pushing this design, trying to think of how you can use this idea of having robots that have internal degrees of freedom that are unactuated, which is important for aerial robots because it reduces your weight, etc., to get more capabilities. And I think inspired by what we sort of see in nature, right? So we have lots of sort of degrees of freedom internally that allow us to move in interesting ways. When we build robots, we tend to do the opposite, right? We like rigid robots that are very predictable, easy to model, but that then potentially reduce the amount of things that they can do. So this is the resulting design. It's still able to fold, but it has no spring. So the previous robot was spring-loaded. This one is not. It's totally passive. And it has some new capabilities that we did not have with the previous design. So I just want to show you what this looks like. Here's a quick preview. The idea is that the arms can fold down, and then the vehicle can fly in this narrow configuration. So the way this works is that as a quadcopter, you need to be able to control your orientation, which requires 3 components of torque, in addition to 1 component of force, so that you can point the vehicle and then push it in the direction. With this folded configuration, we can still achieve the same thing. We're using the arms that are folded down. These are folded down so they don't meet at the center, but they're offset. And this allows us to still get a yaw torque, even if we only have 2 propellers. And then we can transition from normal quadcopter mode to narrow mode, and then also fold all 4 arms down to be a fully compact module like we had with the original design. So here's some things you can do. So you can fly like a quadcopter, and then if you need to fly through a narrow gap, you can trigger this mode transition. Now you are narrow, and then you can fly, you can fit through these spaces that you could not fit through as a normal vehicle. A note here, especially for the vision people, we're totally cheating. We're using mocap for localization. Of course, the interest here is really on the dynamics. But in principle, nothing prevents you from doing this with fully onboard control. Okay, so you can fly through horizontal gaps, you can fly through vertical gaps. So here we just sort of show the vehicle falling through this vertical gap. And the way it does this is it reverses the thrust on the propellers. This folds the propellers in, and then the vehicle becomes very compact, allowing it to fit through these narrow spaces. So here in slow motion, just from looking up from the bottom, we see the vehicle falling and falling through. And as you can imagine, there's a lot of sort of complicated dynamics, etc., happening and high-speed control. This, by the way, is work with Nathan Bucky, who is sitting, so there he is. He's about to graduate. I think he has a job already, but if you want to try and poach him, maybe there's hope. What else can you do with this vehicle? Well, because the arms can fold down, you can perch on objects. So here you'll see the robot taking off and then landing on this wire. And if it turns off the motors, the arms just fall down. And of course, what happens now is the center of mass drops below the contact point, which gives you a natural perch, allowing the vehicle to land and take off. And then lastly, we have load carrying with lots of asterisks, because it only works if your load is particularly light. But it does work, so you can use this configuration to do things like pick up loads. So you'll see here the robots picking up this box. And really the key, or the thing that makes this, I think, interesting is that this still is only a quadcopter. It only has 4 inputs. It only has these 4 motors. So in some sense, it's no more complex than the standard quadcopter that you might have, except that we have all of these additional capabilities. And I'm going over time. So very quickly, some other work we've done. So Karan presented earlier. He was working on these sort of multiple batteries. Just want to present another quick project that we worked on with Karan. How do you make these systems more efficient? With any flying system, this is typically the first constraint you hit: flight time or range or endurance. So the fundamental problem is the mass. And when you're dealing with these electric things, the problem is the low specific energy of batteries. And one of the things that makes batteries challenging is, unlike gasoline that you burn and then eject, you have to carry the battery even after it's depleted. So skipping over some of the details, if you stage your battery, if you have the ability to reduce the battery mass as you consume it, thinking of staging it like you might stage a rocket, you can increase your flight time. So this graph just sort of shows, if you take a drone and you have only a single stage, you cannot see where I'm pointing. You have the blue curve there, and if you now stage your batteries, so if you allow the system to get rid of the battery mass as it is being depleted, you can increase your endurance quite dramatically. So of course, there are some environmental concerns here, so let's bear that in mind. But in principle, this is what it looks like. So what you're seeing here is the drone with 2 batteries. It depletes 1 battery, and then it ejects the battery. The 2 curves show, on the red curve is if you just consume the full battery in one go. The blue curve shows if you stage them, what this performance will look like. Here's just a video showing this in flight, and our time police is chasing me down. So I will stop there and just say, as always, I get to present the cool videos, but the students do all the hard work. Funders, etc. If you are interested in any of this stuff, please go to our research page. All of the publications are there, or just shoot me an email at MWM. Thank you.
Thanks, Mark. So we have a question.
Hi, Mark. I have a question about the dynamic transition. How do you account for what are your thoughts on accounting for any variability in the transition, especially if you're trying to go through a narrow kind of space? Is there any...
Can you say what is the variability? Which variability?
Like, let's say because when you collapse the 2 wings, it kind of like, there's a lot of noise in the system, it seems.
No, it's actually, so yeah, first of all, there's contact dynamics, which Karen will tell us all about how complex that is. So the way we do it is we fold first, and then once we're stable, then we traverse. So as long as you can do that transition somewhere kind of safe, then it's you're not in as much trouble. But of course, and what would be, I think, a really interesting next step is using these sort of transitions dynamically, right? So folding mid-flight to do something interesting. And then, of course, that becomes much more important. And Nathan over there can give you all the extra information.
Actually, one quick follow-up on that. So when this transition happens, do you switch to a new stabilizing policy to make yourself?
So there's different controllers for the different modes. At sort of a high level, they're very similar in structure. The difference is how we generate, given the sort of high-level control objectives, how we generate the motor forces from them. That does change. For each mode, there's a different control structure.
Okay, thanks. Okay, so next we have Grace Gao from Stanford.
Hello, everybody. Good afternoon. It's so exciting to have an in-person conference and see everybody in the 3D space. And then also, thank you for staying late. I know this is the last part. So I'm going to talk about our research on safe autonomous vehicle localization. We know that safety is very important for localization for autonomous vehicles. And safety itself is actually a pretty broad concept. And then even sometimes it's hard to quantify. For our research group, we tackle the safety in these 3 categories. First, we want to ensure the vehicle localization safety against sensing and perception uncertainties. And also, we want to make sure that the vehicle can locate in a safe way under extreme vehicle dynamics. And what's more, when we talk about safety, we have to think about the other side, which is the failures, right? And sometimes the failures are not so easy to deal with because it's hard to find failures in an efficient way, right? And then, because it doesn't happen very often. So we also have this thrust on how to ensure safety and how to find failures. So first, let's talk about the sensing uncertainties. And given that I'm wearing a hat as a faculty member in the aeronautics and astronautics department, and then the good news is that the safety of vehicle localization in aviation has been achieved and then has been continuously being enhanced. For example, if we get on an airplane, we probably feel safe, and then we don't worry too much about the airplane crashing or falling from the sky, right? And then, so how about for autonomous cars, right? Can we actually utilize some of the methods or metrics of safe aviation and then apply that to autonomous driving. So there's a nice metrics called integrity risk. That means we not only need to locate the vehicle accurately, but also need to quantify the confidence of the accuracy, right? So in other words, if you just say, oh, my GPS device can locate me within 5-meter accuracy, but that's not good enough. You need to know that 5-meter accuracy is associated with, like, say, 99.99999 percent of confidence level. So we have our recent work on joint pose and integrity risk estimation using GPS and camera fusion. So in this work, we use a particle filtering framework, and we try to jointly optimize for the pose estimation as well as the integrity risk estimation. And then we have tested our algorithm using the real-world data, the driving data set. And in addition, we emulated added noise in terms of, say, adding Gaussian bias noise to GPS measurements, as well as adding blur and then occlusion to random, to the image inputs, and to further test the sensitivity of our algorithm and then stress testing it. And then as you can see, so our algorithm is a purple color on the right, and then it outperforms the existing methods. So that's about the sensing safety against sensing uncertainty part. So what about safety under extreme dynamics? So people may think, what do you mean by extreme dynamics, right? So let me give you an example. So this is in collaboration with Professor Chris Gerdy's lab. So Professor Gerdy's has done really amazing work of enabling and demonstrating successfully the single car autonomous drifting under control. It's super cool, isn't that? So given that the single car drifting has been successfully demonstrated, so for research, how do we further push the frontier of this localization under extreme high vehicle dynamics? So we want to extend that from a single car drifting to tandem drifting. That means two cars drifting together with the vision of maybe in the future multiple autonomous cars, and they can all drift together safely and under control. So we'll see. So our contribution here is to provide the accurate and robust relative perception and localization between the tandem drifting cars. And then we have done some nice initial work on this, and then Adyasha somewhere here, yeah, right there, and then she gave the spotlight talk. So, okay. So, and then a third category, right, is about how to ensure the safety against failures, right? And then this is actually quite interesting. You may, actually, when I took on this, I didn't realize who would fund this work, and guess what? It's the car insurance companies. Currently for my own car insurance, right, they check my driving record and all this, and then they set a premium about how much I have to pay every month for my car insurance. But in the future, it will be all these autonomous driving cars on the road. And then how do the car insurance companies set the premiums and tell the autonomous driving cars how much they should pay for their car insurance? So they need to better assess the risk for all these autonomous driving cars, and in particular about the failures, right, such as crashing. And then, as I mentioned, finding failures is not easy because it doesn't happen very often, and it's not realistic to drive millions of miles and then to find all these statistics, at least from the research group point of view. So this is I'm also very fortunate to collaborate with Professor Michael Kokendorfer, and then we are trying to find the likely failures, and then our contribution from our group is to incorporate sensing uncertainties in terms of quantifying the risks and finding the failures. And then Shub somewhere, is Shub here? Anyway, so Shub gave a spotlight talk on about, I'm running out of time, so my last slide. So here are some of my other research platforms we use. I lead the nav lab, so we not only navigate cars, but also aerial vehicles and other types of vehicles. And then I'm very fortunate to have the opportunity to work with this wonderful group of students, and we are having a lot of fun together. Thank you.
Okay, we have a question for Grace.
For the great talk. I'm wondering, so here we're doing localization using GPS and camera. How does it compare with doing localization using laser sensor and high definition map?
Yeah, that's a very good question. We also do have research using LiDAR sensors and with the high definition map as well. So it depends on the applications, right? And then different sensors, they have different pros and cons. And sometimes, in the real world applications, it's a matter of the cost, right? And then how much budget the autonomous driving companies want to spend.
A quick follow-up on that. Do you know how much? I assume the GPS plus camera solution is cheaper than the laser plus HD map. Do you know how much saving we would get by using GPS and camera?
Yeah. So that's another good question, right? And then first of all, I think in terms of cost, and things are really changing a lot. For example, a couple years ago, we have this mechanical LiDAR sensor in our research group. We paid close to $8,000 to $10,000 per LiDAR sensor. But recently, there has been solid-state LiDAR sensors. The price tag is on a few $100 level, right? So I think even for the price part, it's changing. And then, so it's I think it's just a lot of parameters there, but there are pros and cons for all these sensors. Yeah.
Thank you.
All right, let's thank Grace.
Thank you.
And then next we have Michael Kokenderfer from Stanford.
Hi, so I'll provide a few highlights from the Stanford Intelligent Systems Laboratory, or SIZL. One publication that came out just a little bit earlier this year, led by Anthony Corso, is this really great survey on black box safety validation for general cyber physical systems. And the framework works like this. You have a system. The system can be a robot, a drone, a car, or whatever. You just need to be able to simulate that system forward. You also need a model of the environment, a probabilistic model of the environment. And then we have an adversary. And what the adversary is trying to do is perturb the environment so that you can find a failure. And it's really important to really characterize the failures in your system at design time before they're deployed in the real world. And so you might have a number of different goals. One might be just find failures or falsification, find a situation where your system fails. Another goal might be to actually find the most likely failures so that you can devote your engineering effort to addressing them. You may also be interested in finding the probability of failure. And there are a number of different algorithmic approaches that have been taken in the literature, and my students have contributed to a number of these categories. One category is adaptive stress testing. And here we have a simulator, and we can model the perception system and the control system and so forth. But we also need a reinforcement learner or some kind of planner, and we use that to find the most likely failure. We published on this last year, but what we've been looking at this year is using the idea of transfer learning. So if you're a place like Waymo, you may continuously evolve your system, and you don't want to restart the validation process with every commit. You want to take what you learned from earlier analyses and try to generalize that to new situations. Or if you're an insurance company like Allstate, you may need to evaluate a number of different systems, and you want to transfer what you learned from across those different systems. And so Anthony Corso looked at an attention mechanism for transferring between these tasks. Another student, Mark Corin, this was in collaboration with NVIDIA. We have a number of low fidelity simulators, and they're nice because we can run them really quickly. But what we would like to do is see how well insights from that generalize to much higher fidelity simulators. What you see here is a screenshot from one of NVIDIA's high fidelity simulators. We've also been working on verification of image-based controllers. You may have seen this domain before. We have, this is called TaxiNet. So we have a video camera mounted on the side of an aircraft. That image gets downsampled, turned to grayscale, and then it's fed into a convolutional neural network, the output being a steering command. And the aim is to keep the aircraft on the runway center line. We've been simulating this in the X-Plane 11 simulator. So very complicated dynamics and so forth. We tried out the controller in a number of different situations, different lighting conditions and so forth, and we found that it very reliably tracks the runway center line. But what we wanted to understand is if there were small image perturbations, is it actually possible to fool the aircraft into driving off the side of the runway? We found that with 3% image perturbation, which is actually not very perceptible, we can actually find a situation where the aircraft goes off the side of the runway. And the way we do this is by combining adaptive stress testing with neural network formal verification tools, such as ReLUplex and the Marabou framework. So that's combining a formal method with a sampling-based approach. More recently, Sydney Katz, Anthony Corso, and Chris Strong have been looking at using our verification tools for the entire system. So in order to do this, we need to go from a low dimensional representation of the state, and we train up a generator. So from that low dimensional representation, we generate an image, and then that gets concatenated with the control network. And we've been using this to find failures in this closed loop system. Of course, we want to make sure that the generator is behaving properly. And so we've tried out a number of different schemes and come up with different validation processes for this. All right, so one last thing. We just, together with my co-authors, Tim Wheeler and Kyle Ray, we just released algorithms for decision making. You can see some of the topics we cover here. Of course, we build up to POM-DPs and also have sections on decentralized POM-DPs and so forth. It's all available at algorithmsbook.com. And in early 2022, you'll be able to get the print version from MIT Press. I'll stop there.
Right. Questions for Michael?
Thank you for your talk. In your black box work to calculate the most likely failure, how easy do you see to connect that approach with control design techniques like optimal control or MPC, or to use the information that you get from your...
Great question. So actually, what we use for the control system, we just need to be able to simulate it. We don't need to peer into it like other white box mechanisms. So regardless of whether the system is, or the control laws or whatever are generated through, optimal control, like, LQG or whatever, it actually doesn't matter. It could be just a bunch of code someone wrote in Python or Julia or C++ or whatever. And it will find those failures. What you get out in the end are actual simulation traces. And then you can go back and study those carefully, and maybe it would suggest changes in maybe some of the gains in your controller and so forth. Thank you.
Thank you.
Okay, I think we have another question from Rika.
Right. You mentioned the use of RL for finding the faults, and it's notorious for doing that, like exploiting the simulation for doing that. But now you're actually using it for that purpose. But I was wondering if you encountered kind of the flip side of it, where there are some faults that are really like hidden, low probability, like hard to get to. And if that's the case, if the standard RL algorithm weren't able to find it, then what else did you explore?
So the question is, if you have very low probability failures?
Yeah, it's basically like it becomes a complicated problem that, let's say, you haven't been able to see the success of just the standard RL that you throw at it. And did you try anything else?
So we've tried deep reinforcement learning as a solver. Originally, when we were exploring this kind of approach, we were using Monte Carlo tree search. And so we can take advantage of a lot of the innovations in RL, including like value function approximation and other kinds of approaches. If the failure that's of interest is like a needle in the haystack, it's not going to be magic, right? In order to find failures in a situation like that, you would probably need to rely upon a white box approach that goes and systematically looks at, inspects the code and so forth. But this has been really successful in a number of domains. We originally developed it for ACAS-X, which is an aircraft collision avoidance system. We had a collaboration through the Center for AI Safety with GE, and we analyzed a flight management system. And we were actually able to find failures that the engineers at GE found to be useful.
That's great, thanks.
All right. Okay, so thank you, Michael. And let's thank all the speakers for this session one more time. Okay. So this brings us to just closing the session of the program. So I just want to thank everyone to show up. It was really awesome to see all of you guys in person and hold bars in person. Really want to thank my co-organizer, Mark Mueller, and also the other awesome co-organizers, Sid, Erdem, Carrie, all the students. It was really wonderful to see you guys all like here at Stanford. So with that, I just want to mention that next year we plan to have bars in person, hopefully without masks, at UC Berkeley, beautiful Berkeley here. And Mark will be chairing the bars next year. So really excited for that. And yeah, with that, have a safe trip back to Berkeley or home. Traffic might be a little bit heavy. You might want to stick around for dinner. Also, Erdem told me that there is food outside and event services really wants us to take them. So take food. Okay, thank you all.